The universe is not what you were told. For decades, we walked through our lives believing we understood the shape of reality. We saw galaxies in textbooks, counted stars in documentaries, nodded along as scientists explained the edges of existence with calm authority. And then, quietly, the numbers stopped making sense. There are not billions of galaxies scattered across the void. There are trillions, 2 trillion at minimum, maybe more. Each one a swirling empire of hundreds of billions of stars, stretching across distances so vast that light itself, moving at 186,000 miles per second, takes tens of billions of years to cross the gap. And here is the part that should unsettle you. That is only what we can see. The observable universe, that 93 billion light-year sphere of space and time we call home, is not the universe. It is just the horizon. Beyond it, past the farthest galaxy we will ever detect, past the last photon that will ever reach our eyes, something continues. We do not know what. We cannot know what. The light from those regions will never arrive. But the math, the models, the sheer relentless logic of cosmology all point to the same conclusion. What lies beyond our view is not empty. It is more galaxies, more storms raging across gas giants the size of 1,000 Earths, more black holes bending space-time into shapes we have no language for. And woven through all of it, perhaps, life. This is a journey to the edge of everything we know and one step past it. 3 hours to explore the cosmos at its most extreme, its most beautiful, and its most incomprehensible. Some of what you are about to hear will comfort you, some of it will not, but all of it is real. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. We live inside a bubble. Not a physical one, not a wall you could touch, or a barrier you might see if you flew far enough in a rocket. A bubble made of time and light, and the speed limit baked into the structure of the universe itself. That bubble has a name. We call it the observable universe, and it is the only version of reality we will ever be allowed to see. The observable universe is roughly 93 billion light-years across. That number gets thrown around a lot in documentaries and textbooks, usually with a bit of dramatic music underneath, and then everyone moves on. But pause there for a second. 93 billion light-years, edge to edge, a sphere centered on Earth, stretching outward in every direction until it hits a boundary that has nothing to do with walls or edges or the end of anything physical. The boundary is just the place where the light runs out of time. Here's the trick, the thing that breaks most people's intuition the first time they hear it. The universe is 13.8 billion years old. You'd think that means light has had 13.8 billion years to travel, so the farthest thing we could possibly see would be 13.8 billion light-years away. That makes sense, that feels fair. Except the universe doesn't play fair. Space itself has been expanding the entire time that light was traveling. A photon leaves a distant galaxy when the universe is young, starts its journey toward Earth, and while it's in transit, the space between here and there stretches. By the time the photon arrives, the galaxy it came from has been carried much farther away by the expansion of space itself. So the light we receive tonight from the edge of the observable universe has been traveling for 13.8 billion years, but the object that emitted it is now more than 46 billion light-years away, and it's still moving. That's not a typo, that's not a misunderstanding. That's just what happens when the thing doing the moving is space itself rather than an object moving through space. Einstein's equations allow it. Observations confirm it. And the result is a universe where the view we get is younger and smaller than the thing we're actually looking at. You are standing on a rock. That rock is called Earth. Earth orbits a star we named the Sun, a middle-aged yellow dwarf star sitting about 2/3 of the way out from the center of a spiral galaxy we call the Milky Way. The Milky Way contains somewhere between 200 billion and 400 billion stars, depending on whose count you trust and how you define a star versus a brown dwarf versus a stellar remnant that used to be a star but isn't anymore. Those stars are not evenly distributed. Most of them cluster in the dense central bulge or along the spiral arms. Our Sun sits in a relatively quiet region between two arms, a cosmic suburb where nothing particularly dramatic is happening. From our vantage point inside the Milky Way, we see the galaxy edge on. That's why it looks like a river of light stretching across the night sky when you're far enough from city lights to actually see it. You're looking through the plane of the galactic disk, through hundreds of billions of stars and clouds of gas and dust, all of it smeared into a glowing band because your eyes can't resolve individual stars at those distances without help. For most of human history, that band of light was the universe. The Milky Way was all there was. Every star you could see, every constellation, every myth and navigation chart, all of it lived inside one galaxy. Then, in the early 20th century, astronomers started noticing fuzzy patches in the sky that didn't behave like stars. Some of them were clouds of gas inside our own galaxy. But a few, the ones that bothered people, were something else. The Great Debate happened in 1920 at the Smithsonian Museum of Natural History. Two astronomers, Harlow Shapley and Heber Curtis, stood in front of an audience and argued about the scale of the universe. Shapley believed the Milky Way was enormous, maybe 300,000 light-years across, and that the fuzzy spiral nebula people kept photographing were just small clouds inside it. Curtis argued the Milky Way was smaller, and those spiral nebulae were separate galaxies, island universes millions of light-years away. Shapley was wrong about almost everything. The Milky Way is about 100,000 light-years across, not 300,000. The spiral nebulae are galaxies. Curtis was basically right, though his distance estimates were too low. But the debate mattered because it was the first time mainstream astronomy seriously considered the possibility that the universe extended far beyond the Milky Way. That shift, from one galaxy to billions, from a cozy bounded cosmos to an unimaginably vast one, happened within a single human lifetime. Edwin Hubble gets the credit for settling it. In 1923, working at the Mount Wilson Observatory with what was then the largest telescope in the world, Hubble identified a type of variable star called a Cepheid in the Andromeda Nebula. Cepheids pulse with a rhythm tied directly to their true brightness. Measure the pulse, and you know how luminous the star actually is. Compare that to how bright it looks from Earth, and you can calculate the distance. Hubble's Cepheid told him Andromeda was at least 900,000 light-years away, far beyond the edge of the Milky Way, far enough that it had to be its own galaxy. That discovery broke the universe open. If Andromeda was a separate galaxy, then so were the other spiral nebulae, and if there were other galaxies, how many? Where did they end? The question shifted from whether the universe was big to how big, and the answer kept getting worse. By the late 1920s, Hubble had made another discovery, one that would reshape cosmology even more dramatically than the first. He noticed that the light from distant galaxies was redshifted. The wavelengths were stretched, shifted toward the red end of the spectrum. And the farther away a galaxy was, the more its light was redshifted. The relationship was linear. Double the distance, double the redshift. That pattern pointed to one conclusion. The universe was expanding, not expanding into anything, just expanding. Space itself stretching, carrying galaxies along with it like raisins in a rising loaf of bread. That meant if you ran the clock backward, the universe got smaller. Keep going, and eventually everything collapses into a single point. A moment of infinite density and temperature where the laws of physics as we understand them stop making sense. We call that moment the Big Bang, though the term was originally coined by astronomer Fred Hoyle as an insult. Hoyle hated the idea. He spent decades trying to prove the universe was eternal and unchanging. He lost. The Big Bang is not an explosion in space. It's an expansion of space. There was no center, there was no edge. Every point in the universe was once the same point, and when things started expanding, they expanded everywhere at once. You can't point to a direction in the sky and say the Big Bang happened over there. It happened here, it happened everywhere. 13.8 billion years ago, give or take a few tens of millions of years depending on which measurement you trust. The evidence for the Big Bang is overwhelming. The expansion Hubble observed, the cosmic microwave background, a faint glow of radiation left over from when the universe cooled enough for light to travel freely, detected in 1964 and mapped in exquisite detail by satellites ever since. The abundance of hydrogen and helium in the universe, which matches exactly what you'd predict if all of it was forged in the first few minutes after the Big Bang. And the large-scale structure of the universe, the way galaxies cluster into filaments and voids, which matches simulations of how matter would clump together under gravity over billions of years. So we know the universe had a beginning, we know it's been expanding ever since, and we know that expansion sets a limit on what we can see. Light travels at a fixed speed, about 300,000 kilometers per second. Nothing in the universe can go faster. That's not a technological limit, it's a law. And it means that information, anything that happened anywhere, can only reach us as fast as light can carry it. If a star explodes 10,000 light years away, we don't see the explosion until 10,000 years later. The light has to cross that distance. During those 10,000 years, as far as Earth is concerned, the explosion hasn't happened yet. Our view of the universe is always delayed, always outdated. We see the Sun as it was 8 minutes ago, the nearest star system, Alpha Centauri, as it was 4.3 years ago, the Andromeda Galaxy as it was 2.5 million years ago, and the farthest galaxies we've ever detected, galaxies sitting near the edge of the observable universe, as they were more than 13 billion years ago, when the universe itself was still in its infancy. That delay creates the bubble. There is a sphere around Earth, centered on us not because we're special, but because we're the observers, beyond which light has not had enough time to reach us yet. That sphere is the edge of the observable universe. It's not an edge in space, it's an edge in time, and it's always growing. Every second, light from slightly more distant regions enters the bubble. The observable universe gets a little bigger, not because the universe itself is growing, though it is, but because we're seeing deeper into it. The farthest thing we can observe is not a galaxy. It's the cosmic microwave background, the afterglow of the Big Bang itself. When the universe was about 380,000 years old, it cooled enough for electrons and protons to combine into hydrogen atoms. Before that moment, the universe was a hot, opaque fog. Photons couldn't travel more than a short distance without slamming into a free electron and scattering. After that moment, space became transparent. Light could finally travel freely. The cosmic microwave background is the light from that transition, stretched by expansion into microwave wavelengths, arriving at Earth from every direction at once. That light has been traveling for 13.8 billion years. the place it came from, is now about 46.5 billion light-years away. That sets the radius of the observable universe. Double it, and you get the diameter. 93 billion light-years, edge to edge, a sphere of everything we can, in principle, ever see. Here's the uncomfortable part. The observable universe is not the universe. It's just the part we have access to. The actual universe, the whole thing, could be vastly larger. It could be infinite. We have no way to know. The observable universe is like standing in the middle of an ocean at night with a flashlight. You can see a circle of water around you, and that's your world. Beyond that circle, there's more ocean. You just can't see it. The flashlight only reaches so far. Some regions of space are moving away from us faster than light, not because they're breaking the speed limit, but because the space between here and there is expanding faster than light can cross it. Those regions are beyond the cosmic horizon. Their light will never reach us, no matter how long we wait. As the universe continues to expand, and as that expansion accelerates, which observations since the late 1990s tell us it is, more and more galaxies will slip beyond that horizon. In trillions of years, if anyone is still around to look, the night sky will be much emptier. Most galaxies will have receded beyond the point where their light can ever catch up. Right now, though, the sky is full. The Hubble Space Telescope spent years staring at a tiny patch of sky, a region so small it would take dozens of them to cover the area of the full moon. That patch looked empty to the naked eye. No bright stars, no obvious galaxies. Hubble pointed its mirror there anyway and left the shutter open for days. What came back was the Hubble Deep Field, an image containing roughly 3,000 galaxies in a single frame. Galaxies of every size, every shape, every age, spirals and ellipticals and irregulars, some of them so distant their light had been traveling for more than 10 billion years. Astronomers did the math. If one tiny patch of sky contains 3,000 galaxies and you cover the entire sky with patches like that, how many galaxies are there in total? Early estimates based on Hubble data put the number at around 100 billion galaxies in the observable universe. That was the figure you'd find in textbooks for years. Then better instruments started finding fainter galaxies, smaller ones that Hubble couldn't see. The estimate climbed. In 2016, a team led by Christopher Consolis at the University of Nottingham published a study suggesting the true number could be as high as 2 trillion galaxies. 2 trillion. That's the number floating around now, though it comes with caveats. Many of those galaxies are small, faint, distant. Some of them may have merged with larger galaxies by now, since we're seeing them as they were billions of years ago. The 2 trillion figure is more of an upper estimate than a hard count, but even if the real number is lower, even if it's only a few hundred billion, the point stands. The universe is full of galaxies, and each of those galaxies contains billions or hundreds of billions of stars. The Milky Way is not special. It's a large spiral galaxy, sure, but there are galaxies much bigger. Andromeda is bigger. IC 10101, a galaxy about 200 million light-years away, is more than 50 times wider than the Milky Way. There are galaxies that make ours look like a dwarf. And there are actual dwarf galaxies, hundreds of them orbiting the Milky Way like moons, each containing only a few billion stars or fewer. The variety is staggering, and every single one of those galaxies, every star inside them, every planet orbiting those stars, all of it sitting inside the same 93 billion light-year bubble. We don't see the universe as it is, we see it as it was. The farther out we look, the further back in time we're seeing. That's not a metaphor, It's a direct consequence of light having a finite speed. When the James Webb Space Telescope looks at a galaxy 13 billion light-years away, it's not looking at a galaxy that exists right now. It's looking at a galaxy that existed 13 billion years ago. That galaxy today, if it still exists, could look completely different. It could have merged with another galaxy. Its stars could have aged and died. We have no way to know. The information hasn't reached us yet. This creates a strange picture of the cosmos. Every shell of distance around Earth corresponds to a different era in the history of the universe. Look nearby, and you see the universe as it is today, or close to it. Look a billion light-years out, and you're seeing the universe as it was a billion years ago. Look 10 billion light-years out, and you're seeing the universe when it was less than a quarter of its current age. The observable universe is not a snapshot. It's a timeline, layered like an onion, with every layer representing a different moment in cosmic history. Humans used to think Earth was the center of everything. Then we realized the sun was just another star. Then we realized the Milky Way was just another galaxy. Then we realized there were billions of galaxies. Every time we thought we'd found the edge or the center or something that made us cosmically significant, the universe said no. You're just here. There's no center. There's no edge. You're inside a bubble, defined by the speed of light and the age of the universe, looking outward at a history written in red-shifted photons. And the thing is, we're still finding new layers, still refining the picture. The 2 trillion galaxy estimate might be revised upward again, or downward. The size of the observable universe will keep growing as light from more distant regions finally reaches us. Our maps will get better, our instruments will get sharper, but the fundamental constraint will never change. We are trapped inside a horizon set by the speed of light and the age of the universe. We can only ever see the past. We can only ever observe a fraction of what's out there. That fraction, though, is extraordinary. Hundreds of billions of galaxies, each a city of stars, trillions of planets, clouds of gas collapsing into new stars at this very moment, though we won't see it for millions of years. Black holes tearing matter apart, galaxies colliding and merging over timescales so long they make human history look like a sneeze. All of it happening right now, somewhere beyond the reach of our telescopes, in the unobservable universe that extends past the bubble we're stuck inside. The observable universe is not small. 93 billion light-years is a distance so large it makes human scales irrelevant. The fastest spacecraft we've ever built would take tens of thousands of years just to reach the nearest star. And that star is a grain of sand on a beach, compared to the scale of the observable universe, but it's still just a bubble, a limited view, the best seat we'll ever get, but still a seat with obstructed sightlines. Which brings us to the next question. If the observable universe is this vast, this full, this violent and strange and ancient, what lives inside it? What kinds of objects and forces and phenomena fill the space between galaxies, between stars, between the light we can see and the horizons we can't cross? Because the canvas is set, the stage is built, 93 billion light-years across, 2 trillion galaxies deep, layered with 13.8 billion years of history. And scattered throughout that canvas, in numbers almost too large to process, are the individual actors, the stars and storms and giants and monsters that make the universe not just big but interesting. That's where we go next. So we've established the canvas, 93 billion light-years of real estate, 2 trillion galaxies, a bubble of light and time centered on a rock where curious apes invented telescopes. That's the scale, that's the backdrop. Now let's zoom in a few hundred orders of magnitude and talk about the stuff that actually fills the space between stars and galaxies, the objects that orbit those stars, the worlds that make up the inventory of the cosmos. Because the universe is not just empty space punctuated by distant pinpricks of light. It's full, and a huge chunk of what fills it is planets, billions upon billions of them, most of which are nothing like Earth. For most of human history, we had exactly one example of a planetary system, ours. The Sun, 8 planets, a handful of dwarf planets, some moons, asteroids, comets, dust. That was the sample size. We built theories about how planetary systems form based on that single data point, which in hindsight is a bit like trying to understand all of human architecture after only visiting one house. You might get some things right, you'll definitely get some things wrong. For decades, astronomers assumed other stars probably had planets. It made sense. Stars form from collapsing clouds of gas and dust, and the leftover material naturally flattens into a disk. Planets should condense out of that disk the way ours did. But assuming something exists and actually finding it are two very different challenges. Planets are small, dim, and sitting right next to objects that are enormous, bright, and loud. Trying to see a planet next to a star is like trying to spot a firefly hovering next to a searchlight from 1,000 miles away. For a long time, we just couldn't do it. The first confirmed detection of an exoplanet orbiting a Sun-like star came in 1995. Two Swiss astronomers, Michel Mayor and Didier Queloz, were using a telescope in southern France to measure the spectrum of a star called 51 Pegasi, about 50 light-years away. They were looking for tiny wobbles in the star's motion, shifts caused by the gravitational tug of an orbiting planet. If a planet is massive enough and close enough to its star, it pulls the star slightly off-center as it orbits. The star and planet actually orbit their common center of mass, and if you watch the star carefully enough, you can see it wobble. That wobble shows up as a periodic shift in the star's spectrum. The light gets slightly redder, then slightly bluer, then redder again, as the star moves toward and away from us. It's called the radial velocity method, and it works. What Mayor and Queloz found was not what anyone expected. The wobble they detected corresponded to a planet roughly half the mass of Jupiter. That part was fine. Jupiter is huge, and a Jupiter-sized planet tugging on a star would produce a detectable signal. The problem was the orbital period. The planet was completing one full orbit every 4.2 days. 4 days. Jupiter takes 12 years to orbit the Sun. This planet was screaming around its star at a distance closer than Mercury is to our Sun, and it was a gas giant. That should not have been possible. The standard model of planetary formation said that gas giants form far from their stars, out where it's cold enough for ice to condense and provide the raw material needed to build a massive core. Once the core is big enough, it gravitationally captures huge amounts of hydrogen and helium from the surrounding disk, ballooning into a giant planet. That process requires cold conditions and a lot of space. You can't build a Jupiter next to a star where temperatures are hot enough to melt rock. At least, that's what the model said. 51 Pegasi b, the planet Mayor and Queloz found, became the first known hot Jupiter. A gas giant orbiting so close to its star that its atmosphere is heated to over 1,000 degrees. The discovery didn't just add a new planet to the list, it broke the list. If hot Jupiters exist, then either planets can form in places we thought they couldn't, or they form far out and migrate inward, spiraling toward their stars over millions of years as they interact with the protoplanetary disk or with other planets. Both possibilities were uncomfortable because they meant our solar system, with its gas giants sitting peacefully in the outer reaches, was not necessarily the default arrangement. It might just be one configuration among many. Mayer and Quelus won the Nobel Prize in 2019. By that point, astronomers had confirmed the existence of more than 4,000 exoplanets. As of now, that number has climbed past 5,000, and it's still growing. The Kepler Space Telescope, launched in 2009, spent years staring at a single patch of sky containing about 150,000 stars. It was looking for transits, tiny dips in a star's brightness, caused by a planet passing in front of it. Every time a planet crosses between its star and Earth, it blocks a small fraction of the star's light. The dip is minuscule, often less than 1%, but Kepler could detect it. Over the course of its mission, Kepler found more than 2,700 confirmed planets and identified thousands more candidates awaiting confirmation. The transit method has a bias. It's much better at finding large planets that orbit close to their stars because those planets block more light and transit more frequently. A planet like Earth, small and far from its star, might only transit once a year and block less than 0.01% of the star's light. A hot Jupiter transits every few days and blocks 1 to 2% of the light. So the early exoplanet catalogues were packed with gas giants, especially hot Jupiters, not because they're the most common type of planet, but because they're the easiest to find. That said, gas giants are common, really common. Current estimates suggest there are billions of gas giant planets in the Milky Way alone. Some orbit close to their stars, roasted by radiation. Others sit farther out in cooler orbits. And as detection methods have improved, astronomers have started finding planets across the entire range of possible sizes and configurations. There are super-Earths, rocky planets with masses several times that of Earth. There are mini-Neptunes, smaller than Neptune but still wrapped in thick atmospheres of hydrogen and helium. There are rogue planets, wandering through interstellar space with no star to orbit. And there are planets orbiting binary stars, circumbinary planets, the kind of worlds where you'd see two suns in the sky if you were standing on the surface. The diversity is staggering. That phrase gets used a lot in exoplanet research, and it's used a lot because it's true. We thought we understood planets. Turns out we understood one system. Everything beyond that has been a surprise. Hot Jupiters are worth pausing on because they represent one of the most extreme planetary environments we've confirmed. These are worlds where the day side is hot enough to vaporize metals, literally. Spectroscopic observations of hot Jupiter atmospheres have detected gaseous iron, titanium, and even silicates. On the night side, it's cooler, though still hot by any reasonable standard, and the temperature difference between day and night drives winds that can reach thousands of kilometers per hour. Material evaporated on the day side gets carried around the planet by these winds and condenses on the night side, where it might rain molten glass or liquid iron depending on the planet's temperature and atmospheric composition. Some hot Jupiters are so close to their stars that they're tidally locked, meaning one side always faces the star and the other side always faces away, the same way the moon is tidally locked to Earth. That creates a permanent day side and a permanent night side, and the boundary between them, the terminator, is where the most violent weather happens. Imagine standing on that boundary, if standing were somehow an option on a gas giant with no solid surface. On one side of you, the sky glows with the unrelenting heat of a star close enough to fill half the sky. On the other side, darkness and slightly less absurd temperatures, and between them, a jet stream that would make Earth's most powerful hurricanes look like a gentle breeze. Observations with the Hubble Space Telescope and more recently the James Webb Space Telescope, have started to map the atmospheres of some of these planets in detail. By watching the planet transit in front of its star and analyzing how the star's light filters through the planet's atmosphere, astronomers can identify the chemical signatures of molecules in the air: water vapor, carbon monoxide, methane, sodium. In some cases, clouds made of aluminum oxide or magnesium silicate. These aren't Earth-like atmospheres, they're chemical soups heated to temperatures that would destroy any known form of life instantly. And then there are the super-Earths. This is a mass category, not a description of habitability. A super-Earth is any planet with a mass between Earth and Neptune, roughly 1 to 10 times Earth's mass. They're called super-Earths because when they were first discovered, astronomers didn't have a better name. Some of them might be rocky, scaled-up versions of Earth with thicker atmospheres and stronger gravity. Others are probably more like mini-Neptunes, with thick envelopes of hydrogen and helium sitting on top of a rocky or icy core. We don't have anything like them in our solar system, which makes them hard to model. Earth is rocky. Neptune is a gas and ice giant. Super-Earths sit somewhere in between, and we're still figuring out what that means. The interesting thing about super-Earths is how common they appear to be. Kepler found them everywhere. They might be the most common type of planet in the galaxy, and yet our solar system doesn't have one. That's either a coincidence or it tells us something about how our solar system formed that makes it unusual. Either possibility is unsettling. Now let's talk about storms, because if there's one thing gas giants do well, it's weather. Earth has hurricanes, tornadoes, thunderstorms. Those are impressive on a human scale. A strong hurricane can span hundreds of kilometers and carry winds over 200 kilometers per hour. That's enough to flatten cities and reshape coastlines. It's terrifying if you're in one. But put that storm on Jupiter and it would barely register as a blip. Jupiter's Great Red Spot is a storm larger than Earth. Not larger than a city, larger than the entire planet. It's an anticyclonic storm, meaning it rotates in the opposite direction from a hurricane in Earth's northern hemisphere. The winds at its edge reach speeds of around 450 kilometers per hour, and the storm has been raging for at least 350 years. We know that because astronomers have been sketching and photographing it since the 1600s. Giovanni Cassini might have observed it as early as 1665. Robert Hooke reported a spot on Jupiter around the same time. The records aren't perfect, and there's debate over whether those early observations are actually the same storm we see today or a predecessor that faded and was replaced. But either way, the Great Red Spot has been a fixture of Jupiter's atmosphere for centuries. What keeps it going? On Earth, hurricanes die when they move over land or lose their connection to warm ocean water. Jupiter doesn't have land. It doesn't have oceans, at least not on the surface. It's a ball of hydrogen and helium with no solid surface to speak of, just layers of gas getting progressively denser and hotter as you descend, until eventually the pressure is so high that hydrogen starts behaving like a liquid metal. The storm draws energy from Jupiter's internal heat and from the dynamics of the planet's atmosphere. There's no friction from a surface to slow it down, no mountains to disrupt the flow, just endless layers of atmosphere, and a storm that has had centuries to settle into a stable configuration. The Great Red Spot is shrinking. Observations over the last century show that it's been getting smaller. In the 1800s, it was large enough to fit 3 Earths inside. Now it's closer to 1 Earth. Why it's shrinking is still an open question. It might be losing energy to smaller storms that interact with it. It might be changing shape as the dynamics of Jupiter's atmosphere shift. Or it might just be part of a long-term cycle that will eventually reverse. Nobody knows. The storm might fade entirely within a few decades, or it might stabilize and persist for another 1,000 years. Jupiter is not in the habit of explaining itself, and the Great Red Spot is just the most famous storm. Jupiter's atmosphere is covered in bands of clouds, jet streams, and smaller storms. The Juno spacecraft, which has been orbiting Jupiter since 2016, has sent back images of storms clustering around the planet's poles in geometric patterns. At the South Pole, 5 storms surround a central storm, all of them locked in a tight configuration that resembles a pentagon. At the North Pole, 8 storms circle a central vortex in a similar arrangement. These aren't temporary weather patterns. They're stable structures that have persisted for years. Earth has nothing like them. Juno also detected lightning on Jupiter, a lot of it. Lightning on Earth forms in thunderstorms when ice particles collide inside clouds and build up static charge. The discharge produces a flash of light and a burst of radio noise. Jupiter's lightning works the same way, but the storms are much larger and the lightning is much more powerful. Juno's instruments picked up radio signals from Jovian lightning at a rate of several strikes per second. Some of those strikes are estimated to be more than 3 times more powerful than the strongest lightning on Earth. Saturn has its own brand of weirdness. At Saturn's North Pole, there's a hexagon. Not a metaphor, not an optical illusion, an actual 6-sided jet stream that wraps around the pole in a near-perfect geometric shape. Each side of the hexagon is about 13,800 kilometers long. The structure is stable. It was first spotted by Voyager in the early 1980s, and when Cassini arrived in 2004, it was still there, unchanged. The hexagon is a standing wave pattern in Saturn's atmosphere, a quirk of fluid dynamics that happens when jet streams interact at specific speeds and latitudes. Scientists have replicated similar shapes in laboratory experiments with rotating fluids, but seeing one on a planetary scale, stable for decades, is something else. Inside the hexagon, at the very center of Saturn's North Pole, there's a massive cyclone. The eye of that cyclone is about 50 times larger than the average hurricane eye on Earth, and the clouds swirling around it have been clocked at speeds over 500 kilometers per hour. Saturn also produces occasional planet-wide storms, massive eruptions of convective activity that can wrap around the entire planet. These great white spots, as they're called, appear roughly once every 30 years. They're driven by seasonal changes as Saturn's axial tilt causes different parts of the atmosphere to heat up during the planet's long year. When a great white spot erupts, it can disrupt Saturn's jet streams for months. Then there are the ice giants. Uranus and Neptune don't get as much attention as Jupiter and Saturn, partly because they're farther away and harder to study, and partly because they're just less visually dramatic. But don't let the name fool you. Ice giant doesn't mean they're frozen solid. It means their interiors contain a lot of water, methane and ammonia, which astronomers collectively call ices, even though at the temperatures and pressures inside these planets, those materials are more like hot, dense fluids than anything you'd scrape off a windshield. Neptune has the fastest winds in the solar system. Winds near Neptune's equator have been measured at over 2,000 kilometers per hour. That's 5 times faster than the worst hurricane Earth has ever produced. Why Neptune, the planet farthest from the Sun and receiving the least solar energy, has the most violent winds is still a mystery. The leading theory is that Neptune's winds are driven by internal heat rather than solar heating, but the details are murky. The planet generates more heat than it receives from the Sun, and that internal energy somehow translates into jet streams that rip through the atmosphere at hypersonic speeds. Both Uranus and Neptune have atmospheres rich in methane, which gives them their blue color. Methane absorbs red light and reflects blue, so when sunlight hits their atmospheres, the light that bounces back is blue. At the low temperatures found in the upper atmospheres of these planets, methane can condense into clouds, and there's been speculation, though not definitive proof, that it might rain methane on these worlds, or even rain diamonds. Under the intense pressure and temperature conditions deeper in the atmosphere, methane molecules could break apart, and the carbon atoms could crystallize into diamond. Those diamonds would then sink through the atmosphere like hail. It's a fun image. Whether it actually happens is still an open question, but the thermodynamics allow for it. Comparing Earth's weather to the weather on gas giants is like comparing a campfire to a forest fire. Sure, they're both fires, but the scale is so different that the comparison barely makes sense. Earth's weather is driven by solar heating, the rotation of the planet, and the distribution of oceans and continents. You get regional differences: deserts, rainforests, polar ice caps. Hurricanes form over warm oceans and dissipate over land. Thunderstorms build up in the afternoon and fade by evening. Everything is temporary, localized, constrained by geography and energy availability. Gas giants have no geography, no land to disrupt a storm, no oceans to provide boundaries, just layers of atmosphere stacked on top of each other, stirred by the planet's rotation and driven by internal heat or tidal forces or both. Storms on gas giants don't dissipate because there's nothing to stop them. They just keep going, fed by a continuous supply of energy, until something disrupts them, or they merge with another storm, or they slowly lose energy over timescales that make human history look like a blink. And these aren't just abstract phenomena happening on distant worlds we'll never visit. They matter because they tell us how planets work, how atmospheres behave under extreme conditions, how energy moves through a fluid system at planetary scales. Every storm on Jupiter is a laboratory experiment we could never replicate on Earth. Every jet stream on Saturn is a data point for understanding fluid dynamics in regimes we can't access in any other way. There's also the question of what all this means for habitability. Gas giants themselves are not habitable. There's no surface, no stable environment. The pressures and temperatures at depth would crush and incinerate anything we'd recognize as life. But gas giants don't exist in isolation. They have moons, lots of them, and some of those moons are very interesting. Jupiter's moon Europa has an ocean of liquid water beneath its ice shell. Saturn's moon Enceladus has geysers erupting from its south pole, spraying water vapor and organic molecules into space. Titan, Saturn's largest moon, has lakes and rivers of liquid methane on its surface and a thick nitrogen atmosphere. None of these environments are Earth-like, but all of them have liquid solvents, energy sources, and complex chemistry. That's enough to make astrobiologists pay attention. The presence of gas giants in a planetary system also affects where habitable zones can exist. A massive planet like Jupiter acts as a gravitational shepherd, clearing out debris from the inner solar system and stabilizing the orbits of smaller planets. Without Jupiter, Earth might have been hit by far more asteroids and comets, possibly sterilizing the surface over and over again before life had a chance to take hold. On the other hand, a gas giant that migrates inward, like a hot Jupiter, could eject or destroy rocky planets in its path, wiping out any chance of habitability in that system. So gas giants are not just interesting because they're big and violent. They're interesting because they shape the architecture of planetary systems. They determine where planets form, where they end up, and whether smaller, rocky worlds have stable enough conditions to develop atmospheres, oceans, and potentially life. And this brings us to the edge of a different kind of question. We've talked about planets, about storms, about atmospheres heated to thousands of degrees and winds faster than sound. But planets, even giant ones, are held together by gravity. They orbit stars, they follow predictable paths, they're governed by forces we understand. But there are objects in the universe where gravity stops being a force you can intuitively grasp and starts behaving like something out of a fever dream. Objects where the rules bend so far that they break. Objects that don't just shape their surroundings, they reshape space itself. Those are next. We just spent time with planets. Gas giants wrapped in storms older than human civilization, worlds where it rains glass sideways at supersonic speeds and winds strong enough to strip continents off their foundations, if those worlds had foundations to strip. Impressive, sure. Violent, absolutely. But planets, even the most extreme ones, are still playing by rules you can understand intuitively. Gravity pulls them into spheres, they orbit stars, they follow predictable paths. You could, in theory, stand on one of Jupiter's moons and watch the great red spot churn overhead, and your brain would still be operating inside a framework of physics that makes sense. Black holes are where that framework stops making sense. They are not holes. That needs to be said up front because the name is misleading and almost everyone gets the wrong picture the first time they hear it. A black hole is not a tunnel, it is not a drain, it is not empty space with a vacuum at the center, pulling things in like a cosmic shop vac. A black hole is an object, a thing. A concentration of matter so dense that it has collapsed in on itself to the point where the gravity it generates is strong enough to trap light. Not bend light, not slow light down, trap it permanently. Light is the fastest thing in the universe. Nothing moves faster. And light, once it crosses a specific boundary around a black hole called the event horizon, cannot get back out. It does not slow down and drift away. It does not get redirected. It is gone. That boundary, that point of no return, is what defines the black hole. Everything inside the event horizon is lost to the rest of the universe forever. Everything outside can, in theory, escape if it is moving fast enough or far enough away. The event horizon is the line where escape velocity equals the speed of light. Cross it, and you are not coming back. Most black holes start as stars, not all stars, just the big ones. Stars more than about 20 times the mass of the Sun. When a star like that runs out of fuel, the core collapses. For its entire life, the star has been held up by the outward pressure of nuclear fusion in its core. Hydrogen fusing into helium, helium into carbon, carbon into oxygen, and so on up the periodic table. Each fusion reaction releases energy, and that energy pushes outward against the crushing weight of the star's own gravity. As long as fusion continues, the star stays stable. When the fuel runs out, the pressure drops, gravity wins. The core collapses in less than a second. Millions of kilometers of stellar material, compressed down to a sphere maybe 30 kilometers across. The outer layers of the star, no longer supported by the core, fall inward and then rebound in a supernova, one of the most violent explosions in the universe. For a few weeks, that single dying star can outshine an entire galaxy. What is left behind, sitting in the center of the explosion, is either a neutron star or a black hole. Neutron stars form when the collapsing core is not quite massive enough to become a black hole. The core compresses until protons and electrons are squeezed together into neutrons, and the pressure from degenerate neutron matter, a state of matter so dense that a sugar cube-sized piece would weigh as much as a mountain, holds the collapse at bay. You end up with a ball of neutrons about 20 kilometers across, spinning rapidly, sometimes hundreds of times per second, with a magnetic field trillions of times stronger than Earth's. Neutron stars are extreme, but they have a surface, they have a structure. You could, in the most technical sense, land on one. You would be crushed and irradiated instantly, but the object itself is still something your brain can picture. Black holes do not give you that courtesy. If the collapsing core is massive enough, nothing stops the collapse. Not neutron degeneracy pressure, not any known force in physics. The matter keeps falling inward until it reaches a point of infinite density and zero volume. A singularity. That word shows up a lot in black hole physics, and it is a polite way of saying the math breaks. General relativity, Einstein's theory of gravity, predicts that all the mass of the collapsing core gets compressed into a single point with no dimensions, infinite density, infinite curvature of space-time. The equations produce infinities, and infinities in physics are usually a sign that you have pushed the theory past the point where it can describe what is happening. Nobody knows what actually exists at the center of a black hole. The singularity is hidden behind the event horizon, so we cannot see it, we cannot measure it, we cannot send a probe to check because anything that crosses the event horizon is gone. No signal gets out. No information escapes. The inside of a black hole is, by definition, unknowable to anyone on the outside. You could argue that makes it irrelevant. If we can never see it or interact with it, does it matter what is happening in there? Philosophically, maybe not. Practically, it drives physicists up the wall because it means the two most successful theories in physics, general relativity and quantum mechanics, are fundamentally incompatible at the one place where they should both apply. The event horizon is not a physical surface. There is no wall, no membrane. If you were falling toward a black hole, you would not feel anything special as you crossed the event horizon. Locally, space would look normal. You could shine a flashlight and watch the beam spread out ahead of you. From your perspective, nothing dramatic happens at the moment you cross, but from the perspective of someone watching you from a safe distance, something very strange happens. As you approach the event horizon, time dilation kicks in. The closer you get, the slower your clock appears to run relative to the outside universe. To someone watching from far away, you appear to slow down, freeze, and then fade as the light from your body gets stretched into longer and longer wavelengths. You never actually appear to cross the horizon. You just asymptotically approach it, getting dimmer and redder until you vanish. Meanwhile, from your point of view, you fall straight through in a finite amount of time. And once you are inside, the singularity is no longer a point in space that you could choose to avoid. It is a point in your future. You are going to hit it the same way you are going to reach next Tuesday. It is not a place, it is a moment. And no amount of thrust or maneuvering will let you avoid it because every direction you could possibly move, including what your instruments tell you is away from the singularity, leads toward it. The singularity is in your future the way tomorrow is in your future, and you cannot stop time from moving forward. That is what general relativity says happens. Whether it is actually true is an open question because nobody has ever tested it, nobody ever will. The event horizon is a one-way door, and the only way to find out what is on the other side is to go through and never come back. Stellar mass black holes, the kind formed from collapsing stars, are relatively small. A black hole with 10 times the mass of the Sun has an event horizon with a radius of about 30 kilometers. You could fit it inside a city. The Milky Way is thought to contain somewhere between 100 million and a billion stellar mass black holes, most of them invisible because they are not currently feeding on anything. A black hole sitting alone in interstellar space does not glow, it does not emit light. It is just a knot of curved space-time drifting through the galaxy, and unless it happens to pass close to a star or a gas cloud, there is no way to detect it. The ones we do detect are feeding. When a black hole is part of a binary system orbiting another star, it can pull gas off the companion star. The gas does not fall straight into the black hole. It has angular momentum, so it spirals inward, forming an accretion disk. As the gas spirals closer to the event horizon, it speeds up. Friction heats it. By the time the gas reaches the inner edge of the accretion disk, just outside the event horizon, it is moving at a significant fraction of the speed of light and heated to millions of degrees. At those temperatures, the gas emits X-rays, bright, high-energy X-rays that we can detect with space-based telescopes. That is how we find most stellar mass black holes, not by seeing the black hole itself, but by seeing the extremely hot gas circling the drain. Cygnus X1 was the first black hole ever confirmed. It is part of a binary system about 6,000 light-years from Earth. Astronomers noticed a bright X-ray source in the constellation Cygnus in the 1960s. Follow-up observations showed that the X-rays were coming from an invisible object orbiting a blue supergiant star. By measuring the star's motion, they calculated the mass of the invisible companion. It came out to about 15 solar masses, too heavy to be a neutron star. The only remaining option was a black hole. Stephen Hawking famously bet physicist Kip Thorne that Cygnus X1 was not a black hole. Hawking lost. He conceded the bet in 1990, and the inscription on the concession document he signed is still one of the most gracious admissions of defeat in the history of science. Stellar mass black holes are fascinating, but they are not the heavy hitters. For that, you need to look at the centers of galaxies. Almost every large galaxy, and a lot of smaller ones, has a supermassive black hole sitting at its core. Not orbiting the center, sitting at the center, the black hole is the anchor. Supermassive black holes range from millions to billions of times the mass of the Sun. The one at the center of the Milky Way, Sagittarius A star, has a mass of about 4 million suns and sits roughly 26,000 light-years from Earth. For decades, astronomers suspected Sagittarius A star was there. They saw stars near the center of the galaxy moving in tight elliptical orbits at speeds that defied explanation unless something extraordinarily massive and compact was sitting in the middle. In the 1990s and 2000s, teams led by Andrea Ghez at UCLA and Reinhard Genzel at the Max Planck Institute tracked individual stars orbiting the galactic center with increasing precision. One star, called S2, completes an orbit around Sagittarius A star every 16 years. At its closest approach, it moves at nearly 5,000 kilometers per second, about 1.7% the speed of light. The only way to make a star move that fast is to put it in orbit around something with a mass of millions of suns compressed into a region smaller than the orbit of Mercury. The observations left no room for doubt. Sagittarius A star is a supermassive black hole. Ghez and Genzel shared the 2020 Nobel Prize in Physics for the work. In April 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole, not Sagittarius A star, a bigger one. The black hole at the center of the galaxy Messier 87, about 53 million light-years away. Messier 87 star, as it is called, has a mass of about 6.5 billion suns. The image shows a bright ring of light surrounding a dark circular region. The dark region is the shadow of the black hole, the area where light has been gravitationally bent so strongly that it either falls into the event horizon or is deflected away from our line of sight. The bright ring is the accretion disk, glowing as gas heats up and spirals inward. The image itself is not a photograph in the traditional sense. The Event Horizon Telescope is not a single telescope. It is a network of radio telescopes scattered across the planet, all pointed at the same target, with their data combined to simulate a telescope the size of the Earth. The technique is called very long baseline interferometry, and it allows astronomers to achieve resolution sharp enough to image the event horizon of a black hole 53 million light-years away. The amount of data processing required to turn the raw observations into that image is staggering. It took years. The final image is blurry by everyday standards, but by the standards of astronomy, it is a miracle. We are looking at the edge of a black hole, the boundary beyond which nothing, not even light, returns. In May 2022, the same team released an image of Sagittarius A star. It looks similar, a bright ring, a dark center. But imaging Sagittarius A star was harder than imaging Messier 87 star, despite the fact that Sagittarius A star is much closer. The problem is size and variability. Messier 87 star is enormous. The region around its event horizon is relatively stable on the timescale of days, so the team could collect data over multiple observation runs and combine them. Sagittarius A star is smaller. The gas in its accretion disk orbits much faster, and the brightness changes on timescales of minutes. The team had to develop new techniques to account for that variability and reconstruct an image from data that was shifting in real time. Both images confirmed what general relativity predicted. The shape of the shadow matches the theoretical predictions almost exactly. That is a win for Einstein. But the images also raise questions. Supermassive black holes are huge. Messier 87 star has an event horizon with a diameter of about 24 billion kilometers. Light would take more than a day to cross it. Sagittarius A star is smaller but still enormous by any reasonable standard. The question is, how did they get that big? A black hole grows by eating. It can consume gas, dust, stars, other black holes, anything that gets too close. The problem is that it takes time. A black hole feeding at the maximum possible rate, a limit called the Eddington limit, where the outward pressure of radiation from the infalling material balances the inward pull of gravity, can roughly double its mass every 50 million years. That sounds fast until you realize the universe is only 13.8 billion years old. Start with a stellar mass black hole of 10 solar masses. Let it feed at the Eddington limit for the entire history of the universe, and you still do not get anywhere close to 1 billion solar masses. The math does not work. So how did supermassive black holes grow so large so fast? There are a few possibilities. One is that they started bigger. Maybe in the early universe, clouds of gas collapsed directly into massive black holes without forming stars first. These seeds, perhaps 100,000 or 1 million solar masses, would have a head start. Grow from there, and you can reach supermassive scales in the time available. Another possibility is mergers. Galaxies collide and merge. When they do, their central black holes eventually spiral together and merge into a single larger black hole. Do that enough times, and you build up a monster. Both processes probably happened. The trouble is, we have found supermassive black holes in the early universe, seen as they were less than 1 billion years after the Big Bang, that are already billions of solar masses. That is not enough time for either process to work comfortably. The black holes grew faster than the models predict they should have, which means something about our understanding of black hole growth or the conditions in the early universe is incomplete. Supermassive black holes are not just sitting quietly at the centers of galaxies. Some of them are active, violently active. When a supermassive black hole is feeding on a large amount of gas, the accretion disk heats up and glows intensely across the entire electromagnetic spectrum, from radio waves to gamma rays. The energy output can exceed that of the entire galaxy. These are called active galactic nuclei, and they come in different flavors depending on the viewing angle and the amount of material being consumed. Quasars are the brightest type. Quasar is short for quasi-stellar object because when they were first discovered in the 1960s, they looked like stars in photographs but had spectra that made no sense. It took years to figure out that they were extremely distant galaxies with supermassive black holes at their centers blazing so brightly that they outshine every star in the host galaxy combined. Some active galactic nuclei produced jets, narrow beams of particles and radiation blasted out along the black hole's rotation axis at speeds close to the speed of light. These jets can extend for millions of light years, far beyond the galaxy itself, carving through intergalactic space and lighting up enormous clouds of gas. The mechanism that launches the jets is still not fully understood. It involves the interaction between the black hole's spin, the magnetic fields threading through the accretion disk, and the intense radiation pressure near the event horizon. The details are messy and the simulations are hard, but the result is clear. Black holes do not just consume, they also eject. They are messy eaters, and the leftovers get flung outward at relativistic speeds. Black holes warp space. That is not a metaphor. General relativity describes gravity not as a force, but as the curvature of space-time caused by mass and energy. A planet curves space-time a little, a star curves it more. A black hole curves it so much that space-time folds in on itself. Light traveling near a black hole follows the curves. If you were watching a black hole with a star directly behind it from your perspective, you would not see the star disappear. You would see the star's light bent around the black hole, creating a ring of light called an Einstein ring. This is gravitational lensing, and it happens around any massive object, but black holes produce the most dramatic examples because the curvature is so extreme. Gravitational lensing is useful. Astronomers use it to study distant galaxies that would otherwise be too faint to see. A massive galaxy or a black hole sitting between Earth and a distant object can magnify the background object's light, effectively turning the foreground mass into a natural telescope. Some of the farthest galaxies ever observed were only detectable because a foreground cluster of galaxies lensed their light. Stephen Hawking made a career out of thinking about black holes, and in 1974 he published a paper that shook the field. He showed, using a mix of general relativity and quantum mechanics, that black holes should not be completely black. They should emit a faint glow of radiation, now called Hawking radiation, because of quantum effects near the event horizon. The details involve virtual particles popping into existence near the horizon, with one particle falling in and the other escaping. But the upshot is that black holes slowly lose mass over time. They evaporate. This is weird for two reasons. One, it means black holes have a temperature. A black hole with the mass of the Sun would have a temperature of about 60 nanokelvins, far colder than the cosmic microwave background, so it would actually absorb more energy than it radiates and grow rather than shrink. But smaller black holes are hotter. A black hole with the mass of a mountain would have a temperature high enough to glow visibly. A black hole with the mass of a large asteroid would evaporate in a burst of radiation within seconds. 2. And this is the part that still bothers physicists. Hawking radiation suggests that information is destroyed when something falls into a black hole. Quantum mechanics says information cannot be destroyed. General relativity via Hawking's calculation says it is. This is the black hole information paradox, and it has been one of the biggest unresolved problems in theoretical physics for 50 years. There are ideas, lots of ideas. Maybe the information is encoded in the Hawking radiation in a way we do not yet understand. Maybe it is stored on the event horizon in a holographic form. Maybe black holes do not destroy information, but hide it in a way that makes it effectively inaccessible. Or maybe general relativity breaks down before you reach the singularity and something else, some theory of quantum gravity we have not discovered yet, takes over and saves the information. Nobody knows. The paradox remains. There are wilder ideas floating around, wormholes, white holes, hypothetical structures that pop up in the equations of general relativity but have never been observed. A wormhole is a tunnel through space-time connecting two distant points, fall into one end, emerge from the other, potentially in a completely different part of the universe. General relativity allows them mathematically, but every analysis suggests they would be unstable and collapse instantly unless held open by exotic matter with negative energy density which may not exist. White holes are the time-reversed version of black holes. Instead of pulling everything in, they spit everything out. Nothing can enter a white hole. Everything inside is ejected. Again, the equations allow them, but nobody has ever seen one, and it is not clear how they would form. These ideas live mostly in the realm of speculation and science fiction. They are fun to think about. They show up in movies. They make for good conversation. But they are not part of mainstream astrophysics because there is no evidence for them. Black holes, the regular kind, are real. We have imaged them. We have measured their masses. We have watched stars orbit them. They are confirmed, observed, studied objects. Wormholes and white holes are mathematical curiosities unless and until someone finds one. Black holes shape galaxies, not just by sitting at the center and looking menacing. Actively. The jets and winds driven by active galactic nuclei can blow gas out of a galaxy, shutting down star formation. The radiation from the accretion disk can heat the surrounding gas, preventing it from cooling and collapsing into new stars. Supermassive black holes regulate how galaxies grow. In the early universe, galaxies formed stars at a prodigious rate. Then something slowed them down. In many cases, that something was the black hole at the center turning on, heating or ejecting the gas, and starving the galaxy of the raw material it needed to keep building stars. The relationship between the mass of a galaxy's central black hole and the mass of the galaxy itself is surprisingly tight. Bigger galaxies have bigger black holes, and the ratio holds across a wide range of galaxy types. That suggests the black hole and the galaxy grow together, influencing each other in ways we are still working out. The universe is full of black holes, millions in the Milky Way alone, billions across the observable universe, most of them silent, some of them screaming. They are not monsters lurking in the dark, waiting to devour unwary spacecraft. They are objects. Dense, extreme, bizarre objects that happen to be the endpoints of stellar evolution and the anchors of galaxies. They follow rules. Those rules are strange, and some of those rules produce results that feel like they should not be possible, but they are consistent, testable, predictable within the framework of general relativity, and they are everywhere. Every large galaxy has one. That means every one of the 2 trillion galaxies in the observable universe likely has a supermassive black hole at its core. 2 trillion galaxies, 2 trillion black holes, most of them millions or billions of times the mass of the Sun. All of them warping space-time. All of them shaping the galaxies around them. All of them, in a very real sense, acting as architects of the large-scale structure we see when we look out at the universe. Because galaxies are not random, they are not scattered uniformly through space. They cluster, they form groups and filaments and superclusters. And at the heart of almost every one of them sits a black hole that helped determine how it grew, how it evolved, and what it looks like today. Those galaxies, those 2 trillion island universes, are where we turn next. We just spent time with black holes. Objects so dense they fold space in on itself, where the rules stop behaving and the math spits out infinities. Monsters at the centers of galaxies, anchoring everything around them, warping the fabric of reality just by existing. Impressive, terrifying. But here's the thing, black holes, even supermassive ones, are individuals, single objects. They sit at a point in space and they do their thing. They are the punctuation marks in a much larger sentence. Now we need to pull back and look at the sentence itself, because the universe is not a collection of isolated objects scattered randomly through empty space. It is organized, structured, and the organizing principle, the thing that connects everything from the smallest dwarf galaxy to the largest supercluster, is gravity. Gravity and time and 2 trillion islands of stars spread across 93 billion light-years of observable space. This is the story of galaxies. Not one galaxy, all of them, the whole empire. Let's start with the number, because it is the number everyone remembers. 2 trillion galaxies. That figure gets tossed around in documentaries and articles with the same casual confidence people use when citing the speed of light or the number of planets in the solar system. It sounds precise, it sounds authoritative, and it is, to be clear, a reasonable estimate based on solid observational work. But it is not a hard count. Nobody has gone through the universe with a clipboard and tallied every galaxy by hand. What astronomers did was take deep images of small patches of sky, count the galaxies in those patches, and then extrapolate to the entire observable universe. The Hubble Space Telescope spent years doing this. The Hubble Deep Field, the Ultra Deep Field, the Extreme Deep Field. Each survey went deeper, stared longer, found fainter galaxies, and each time the number went up. The 2 trillion estimate came from a study published in 2016 by a team led by Christopher Consoles at the University of Nottingham. They combined data from Hubble and other telescopes, used statistical models to account for galaxies too faint to detect directly, and arrived at a figure roughly 10 times higher than earlier estimates. 2 trillion galaxies in the observable universe, most of them small, most of them faint, most of them invisible to anything except the most sensitive instruments pointed at the sky for days at a time. The headline grabbed attention, the number stuck, and for a few years, 2 trillion was the answer you would get if you asked an astronomer how many galaxies exist. More recent analyses have complicated that picture. Better image processing techniques, better understanding of how galaxy luminosity functions work, and deeper surveys with newer instruments have led some researchers to revise the number downward. Maybe it is closer to a few 100 billion. Maybe the 2 trillion figure overcounted faint galaxies by assuming they were more common than they actually are. The debate is ongoing. The point is, the exact number is uncertain. What is not uncertain is that there are a staggering number of galaxies out there. Whether the true count is 200 billion or 2 trillion, the universe is full. Far fuller than the night sky would ever suggest if you just looked up without a telescope. Galaxies come in types, shapes, flavors. Edwin Hubble, the same astronomer who figured out the universe was expanding, also developed the first widely used classification scheme for galaxies in the 1920s. He divided them into 3 main categories based on their appearance: spirals, ellipticals, and irregulars. The scheme has been refined over the decades, but the basic structure still holds. Spirals are the ones that show up in posters and textbooks, flat disks with bright spiral arms curling out from a central bulge. The Milky Way is a spiral galaxy, specifically a barred spiral, meaning it has a bar-shaped structure of stars running through its center with the spiral arms attached to the ends of the bar. From our position inside the disk, we cannot see the spiral structure directly, but observations of stars and gas in other parts of the galaxy, combined with models of galactic dynamics, tell us it is there. Spiral galaxies are active. They contain a lot of gas and dust, and that gas is constantly collapsing into new stars. The spiral arms are not fixed structures. They are not solid. They are density waves, regions where stars and gas pile up temporarily as they orbit the galactic center. Think of a traffic jam on a highway. The jam itself does not move, but cars flow through it. Spiral arms work the same way. Stars move in and out of the arms as they orbit, and the arms persist as waves of density sweeping around the galaxy. The bright blue light you see in the arms comes from young, massive stars. Those stars are short-lived, so they do not have time to drift far from where they formed. The arms are where star formation is happening right now, and the massive stars that result light up the arms like neon signs. Elliptical galaxies are the opposite. They are smooth, featureless, and old. No spiral arms, no obvious disk structure. Just a roughly spherical or ellipsoidal blob of stars. Ellipticals contain very little gas and dust, which means they are not forming many new stars. Most of the stars in an elliptical galaxy are old, red, and dim. The galaxy itself can be enormous. The largest galaxies in the universe are giant ellipticals sitting at the centers of massive galaxy clusters. These galaxies often formed through mergers, the gradual consumption and combination of smaller galaxies over billions of years. When two spiral galaxies collide, the result is usually an elliptical. The disks get disrupted, the gas gets used up in a burst of star formation or ejected entirely, and what is left is a jumble of stars orbiting in random directions with no coherent structure. Irregular galaxies are the misfits. They do not fit neatly into spiral or elliptical categories. They have chaotic shapes, often because they have been disturbed by gravitational interactions with other galaxies. The Large and Small Magellanic Clouds, two small galaxies visible from the southern hemisphere, are irregular galaxies. They are satellites of the Milky Way, orbiting our galaxy and being slowly pulled apart by its gravity. Over time, the Milky Way will likely consume them entirely. That is how large galaxies grow. They eat their neighbors. Then there are dwarf galaxies, and this is where the numbers get interesting. Dwarf galaxies are small, containing anywhere from a few million to a few billion stars. For comparison, the Milky Way has a few 100 billion stars. Dwarf galaxies are faint. Many of them are so faint they were not discovered until recently because they simply did not show up in surveys. But they are everywhere. Most galaxies in the universe are dwarfs. The Milky Way has dozens of known dwarf satellite galaxies orbiting it, and there are probably more that we have not found yet because they are too faint or too far away. Dwarf galaxies matter because they represent the building blocks of larger galaxies. In the early universe, galaxies formed from the collapse of gas clouds inside dark matter halos. Those first galaxies were small. Over time, they merged and grew into the larger galaxies we see today. Dwarfs are the leftovers, the ones that did not merge, and by studying them, astronomers can learn about the conditions in the early universe and the process by which galaxies assemble. So you have spirals, ellipticals, irregulars, and dwarfs, four broad categories. Within those categories, there is enormous variation. Some spirals have tightly wound arms, others have loose, open arms. Some ellipticals are nearly spherical, others are stretched into elongated shapes. The diversity is staggering, and every galaxy tells a story about its history, how it formed, what it has been through, whether it has collided with other galaxies, whether it is actively forming stars, or whether it exhausted its gas supply billions of years ago and is now coasting. Galaxies are not scattered randomly through space. They cluster. They form groups and clusters and superclusters, all connected by vast filaments of gas and dark matter. This is the cosmic web, the large-scale structure of the universe. If you could step outside the observable universe and look at the whole thing from a distance, you would not see a smooth, uniform distribution of galaxies. You would see a web. Filaments of galaxies stretching across hundreds of millions of light-years, intersecting at dense nodes where galaxy clusters sit. Between the filaments there are voids, enormous empty regions where almost no galaxies exist. The voids are not completely empty. There is gas, dark matter, the occasional lonely galaxy, but compared to the dense regions, the voids are deserts. The cosmic web formed because of gravity and dark matter. In the moments after the Big Bang, the universe was almost perfectly smooth. Almost. There were tiny fluctuations in the density of matter, small regions where there was slightly more stuff, and small regions where there was slightly less. Those fluctuations were imprinted in the universe when it was less than a second old, and they have been growing ever since. Gravity amplifies density differences. Regions with slightly more matter pull in surrounding material, becoming denser. Regions with slightly less matter lose material, becoming emptier. Over billions of years, this process carved the universe into the web-like structure we see today. Dark matter, which does not interact with light but does interact gravitationally, played a crucial role. Dark matter clumps faster than normal matter because it does not feel pressure or radiation. It just collapses under its own gravity, forming halos. Normal matter falls into those halos, cools, and eventually forms stars and galaxies. The first galaxies formed inside dark matter halos somewhere between 100 million and a few hundred million years after the Big Bang. This is the era James Webb is currently exploring, and it is the era where things get weird because the galaxies Webb has found are bigger and brighter than they should be given the time available. That was covered earlier. The point here is that galaxies have been around for nearly the entire history of the universe. 13.8 billion years is a long time, and galaxies have spent most of that time growing, evolving, colliding and merging. Galaxy formation starts with gas, primordial hydrogen and helium left over from the Big Bang. That gas drifts through space, cools, and eventually collapses under gravity inside a dark matter halo. Once the gas gets dense enough, stars begin to form. Early galaxies were small and chaotic, full of young, massive stars burning through their fuel in a few million years and then exploding as supernovae. Those explosions enriched the surrounding gas with heavier elements, carbon, oxygen, iron, the building blocks of planets, and eventually life. Over time, the galaxies grew. They pulled in more gas from their surroundings. They merged with other small galaxies. Stars formed, aged, and died. The galaxies became more structured, more organized. Spirals developed disks and arms. Ellipticals grew into smooth, massive systems, and all of it happened over billions of years. Galaxy collisions are common, not common in the sense that you can watch one happen in real time. Galaxies are huge, and even though they move at hundreds of kilometers per second relative to each other, a collision still takes hundreds of millions of years to play out. But on cosmic timescales, collisions happen all the time. The Milky Way is going to collide with Andromeda. That is not speculation. That is an observed fact. Andromeda is currently about 2.5 million light-years away, and it is heading toward us at about 110 kilometers per second. In roughly 4 to 5 billion years, the two galaxies will merge. The collision will not be gentle. The gravitational interaction will distort both galaxies, flinging stars into new orbits, triggering bursts of star formation as gas clouds collide and compress, and eventually producing a single, larger galaxy. Astronomers have already given it a nickname, Melkomeda, creative, right? The Sun will likely survive the merger. Direct collisions between stars are extremely rare even during galaxy collisions because stars are tiny compared to the distances between them. Space is mostly empty, but the Sun's orbit will change. It might get flung into a different part of the merged galaxy, farther from the center or closer in. Earth will still be orbiting the Sun, assuming it has not been swallowed when the Sun becomes a red giant in about 5 billion years, which is a separate issue. From Earth's perspective, if anyone is still around to watch, the night sky will change dramatically. Andromeda will grow larger and larger over millions of years until it fills the sky. Then the two galaxies will interpenetrate, pass through each other, fall back together and merge. The process will repeat a few times before the galaxies finally settle into a single elliptical-like structure. It will be spectacular. It will also be slow enough that no single human lifetime would capture more than a snapshot of the event. The Milky Way has been involved in collisions before. It is currently in the process of consuming several smaller galaxies. The Sagittarius dwarf elliptical galaxy is being torn apart by the Milky Way's gravity, and its stars are being absorbed into the galactic disk. Evidence of past mergers shows up in the structure of the Milky Way's halo and in streams of stars that wrap around the galaxy in unusual orbits. Those streams are the remnants of dwarf galaxies that got too close and were shredded by tidal forces. This is how large galaxies grow. They are not static, they are constantly eating their neighbors. Galaxy clusters are the densest regions of the cosmic web. A galaxy cluster can contain hundreds or even thousands of galaxies packed into a region a few million light-years across. The Virgo cluster, the nearest large cluster to us, contains over 1,000 galaxies and sits about 54 million light-years away. The Coma cluster, farther out, contains thousands of galaxies. At the centers of these clusters, you often find giant elliptical galaxies that have grown to enormous sizes by cannibalizing other galaxies in the cluster. These brightest cluster galaxies, or BCGs, are some of the largest galaxies in the universe. The space between galaxies in a cluster is not empty. It is filled with hot gas, plasma heated to tens of millions of degrees by the gravitational energy of the cluster. This intra-cluster medium contains more mass than all the stars in all the galaxies in the cluster combined. The gas glows in X-rays, and X-ray telescopes like Chandra have mapped it in detail. The hot gas plays a role in regulating star formation in cluster galaxies. When a galaxy moves through the intracluster medium, the gas in the galaxy can be stripped away by a process called ram pressure stripping. Lose your gas, and you cannot form new stars. Many galaxies in dense clusters are red and dead, full of old stars with no new star formation because they lost their gas long ago. Dark matter holds it all together. Galaxy clusters are so massive that the gravity from the visible matter alone, stars and gas, is not enough to hold them together. They should fly apart. They do not. The only way to explain the observed dynamics is to add a lot of invisible mass. Dark matter. Dark matter halos surround galaxies and galaxy clusters, providing the gravitational scaffolding that keeps everything bound. We cannot see dark matter. It does not emit, absorb, or reflect light. We only know it is there because of its gravitational effects. Stars orbit galaxies faster than they should based on the visible mass. Galaxies in clusters move faster than they should. Light from background galaxies is bent more strongly by foreground clusters than the visible mass can account for. All of these observations point to the same conclusion. There is 5 times more dark matter in the universe than normal matter. What is dark matter? Nobody knows. The leading candidate is a type of particle that interacts only through gravity and possibly the weak nuclear force. WIMPs, or weakly interacting massive particles, have been the favorite for decades. Despite years of searching, nobody has directly detected a WIMP. Other candidates include axions, stereo neutrinos, and more exotic possibilities. The search continues. Dark matter is one of the biggest unsolved problems in physics, and solving it would require either detecting the particle directly or coming up with a completely different theory of gravity that explains all the observations without invoking invisible matter. So far, the invisible matter explanation works better, but the lack of direct detection is frustrating. Then there is dark energy. Dark energy is even stranger than dark matter because it does not clump, it does not form halos, it does not hold galaxies together, it does the opposite, it pushes space apart. In the late 1990s, 2 teams of astronomers studying distant supernovae discovered that the expansion of the universe is accelerating, not slowing down, which is what everyone expected, but speeding up. The only way to explain that acceleration is to introduce a new component to the universe, something with negative pressure that pushes outward against gravity. That something is dark energy, and it makes up about 68% of the total energy density of the universe. Dark matter makes up about 27%. Normal matter, everything we can see, stars, galaxies, planets, people, makes up less than 5%. Dark energy does not affect the motion of galaxies directly on small scales. Gravity still dominates within galaxy clusters, but on the largest scales, dark energy determines the fate of the universe. If dark energy remains constant, the universe will continue expanding forever, and eventually galaxies outside our local group will recede beyond the cosmic horizon. Billions of years from now, the night sky will be much emptier. Most galaxies will have moved so far away that their light can no longer reach us. If dark energy gets stronger over time, a possibility that some models allow, the universe could end in a big rip, where the accelerating expansion eventually tears apart galaxies, stars, planets, and eventually atoms. If dark energy weakens or reverses, the universe could stop expanding and collapse in a big crunch. Right now, all evidence points to a universe that expands forever, cooling and darkening as galaxies drift apart. The large-scale structure of the universe is a product of billions of years of gravitational evolution guided by dark matter and opposed, on the largest scales, by dark energy. It is a ballet, a slow, vast, silent dance of trillions of galaxies moving through a web of filaments and voids, clustering together, colliding, merging, and being pulled apart by the expansion of space itself. The motions are predictable in a statistical sense. Simulations of structure formation, which start with the conditions in the early universe and evolve them forward using gravity and dark matter, reproduce the observed large-scale structure remarkably well, but on smaller scales, every galaxy has its own history, its own story. Edwin Hubble once said, "Equipped with his 5 senses, man explores the universe around him and calls the adventure science." That line gets quoted a lot, and it works because it captures something true. We are small, our senses are limited. We cannot see dark matter. We cannot see dark energy. We can barely see most of the galaxies that exist because they are too faint or too far away. But we can infer, we can measure, we can build instruments that extend our senses and models that extend our understanding. And from that, we have built a picture of a universe far larger, far older, and far stranger than anything our ancestors imagined. 2 trillion galaxies, maybe more, maybe fewer. The exact count will be refined as telescopes get better and surveys go deeper. But the number is not the point. The point is that the universe is full. Every patch of sky, no matter how dark it looks, contains galaxies, hundreds of them, thousands of them, each one a collection of billions of stars. Each star potentially surrounded by planets, and on at least one of those planets, around one of those stars, in one of those galaxies, something interesting happened. Life. That is not a guess. That is a fact because we are here. The question is whether it happened anywhere else. Whether the chemical accident that produced self-replicating molecules on Earth is common or rare, whether we are alone in this vast empire of galaxies or whether life, in some form, is scattered throughout the cosmos like stars are scattered through a galaxy, that question, the question of life, is where we go next. We just spent time with galaxies, 2 trillion of them scattered across the observable universe like cities of stars, each one its own island of light drifting through the cosmic web. We talked about structure and scale and the forces that shape empires spanning billions of light years, all of it enormous, all of it distant, all of it, from a certain perspective, dead. Stars burn, black holes consume, galaxies collide, but none of that requires consciousness, none of it requires awareness, none of it, as far as we can tell from here, is alive, except for one tiny exception, one pale blue dot orbiting an average star in an unremarkable corner of a spiral galaxy where, for reasons nobody fully understands, chemistry became biology and rocks became us. The question is whether that exception is unique. Whether Earth is the only place in the universe where matter woke up and started asking questions, or whether life, in some form, is scattered throughout the cosmos, hiding in the shadows of those 2 trillion galaxies. That question, the question of whether we are alone, is what drives the search for habitable worlds, and the search starts not with galaxies but with planets. Specifically, planets in the habitable zone. The habitable zone is a simple idea with a misleading name. It is the range of distances from a star where liquid water could exist on the surface of a rocky planet, not too close, where water would boil away, not too far, where it would freeze solid, just right. The name habitable zone suggests that if you find a planet inside it, you have found a habitable planet. That is not true. The habitable zone is a necessary condition, not a sufficient one. You can be in the habitable zone and still be completely uninhabitable. Venus proves that. Venus sits at the inner edge of the Sun's habitable zone. It is the right distance for liquid water. It does not have liquid water. It has a surface temperature of 470 degrees Celsius, hot enough to melt lead, and an atmosphere so thick and toxic that the pressure at the surface is 90 times what you experience standing at sea level on Earth. Soviet probes that landed on Venus in the 1970s lasted about an hour before they were crushed and cooked. Venus is technically in the habitable zone. Venus is hell. Mars sits near the outer edge of the habitable zone. It is cold, dry, and has almost no atmosphere. The surface pressure is less than 1% of Earth's. Liquid water cannot exist on the surface under those conditions. It either freezes or sublimates directly into vapor. Mars might have had liquid water billions of years ago when its atmosphere was thicker and the planet was warmer. Now it is a frozen desert. Also technically in the habitable zone, also not habitable, at least not without a lot of engineering. Earth is in the middle of the habitable zone. It has liquid water on the surface. It has a thick enough atmosphere to maintain pressure and trap heat. It has a magnetic field that shields the surface from solar radiation. It has plate tectonics that recycle nutrients and regulate the climate over geological timescales. And it has life. Lots of life. Everywhere you look, from the deepest ocean trenches to the upper atmosphere to kilometers beneath the surface in solid rock, life has found a way to exist. Earth is not just in the habitable zone, it is habitable. The difference matters. The habitable zone is not a fixed ring. It depends on the star. A small, cool red dwarf star does not put out much energy, so its habitable zone is much closer in, maybe only a few million kilometers from the star. A large, hot blue star pumps out enormous amounts of energy, so its habitable zone is farther out, tens or hundreds of millions of kilometers. The habitable zone also changes over time because stars evolve. The Sun is about 30% brighter now than it was when it first formed. That means Earth was closer to the inner edge of the habitable zone 4 billion years ago. In another billion years, as the Sun continues to brighten, Earth will move to the inner edge and eventually past it. The oceans will boil. The surface will become uninhabitable. Life on Earth, assuming we do not leave or solve the problem somehow, has about 1 billion years left. That sounds like a long time. It is a long time. But it is not infinite. The habitable zone moves, and planets do not. When astronomers talk about finding habitable planets, they mean finding rocky planets in the habitable zone of their star. Rocky matters because gas giants do not have surfaces. You cannot have liquid water on a surface that does not exist. You need a solid planet with a solid surface and an atmosphere that allows liquid water to pool. Earth, Venus and Mars are rocky planets. Jupiter, Saturn, Uranus and Neptune are not. The distinction is fundamental, and for decades we only knew of rocky planets in one system, ours. We had no idea whether rocky planets were common or rare. No idea whether Earth-sized planets existed around other stars. No idea whether habitable zones were empty or full. Then we started finding exoplanets, and the picture changed. The first confirmed exoplanet around a Sun-like star was 51 Pegasi b, discovered in 1995. A hot Jupiter orbiting its star every 4 days. Not habitable, not even close. The early exoplanet discoveries were almost all gas giants because those were the easiest to find. Large planets close to their stars produce strong signals. Small rocky planets farther out produce weak signals. The detection methods had biases, and for years the exoplanet catalogue was full of gas giants and hot Jupiters and not much else. The Kepler Space Telescope changed that. Kepler launched in 2009 with a simple mission: stare at one patch of sky containing about 150,000 stars and watch for transits. A transit happens when a planet passes in front of its star from our perspective, blocking a tiny fraction of the star's light. The dip is small, often less than 1%, but Kepler could detect it, and Kepler stared for years. By the time the mission ended, Kepler had found thousands of planets. Gas giants, yes, but also super-Earths, mini-Neptunes, and rocky planets closer to Earth size. The catalogue went from a few dozen planets to thousands, and the statistics started to make sense. Planets are common, really common. Every star in the Milky Way probably has at least one planet. Some have many. Do the math, and you get a number in the ballpark of 100 billion planets in the galaxy. Maybe more, maybe fewer, but the order of magnitude is right. Planets are not rare. Finding planets is one thing. Finding habitable planets is harder. Kepler found several candidates. Rocky planets, roughly Earth-sized, sitting in the habitable zones of their stars. Kepler 452b, Kepler 186f, Kepler 62e. The names are not memorable. The planets might be. Each one is a world where liquid water could, in principle, exist on the surface, Whether it actually does is unknown. Kepler could tell you the size of the planet and its distance from the star. It could not tell you whether the planet has water, an atmosphere, or anything else that would make it interesting from a habitability standpoint. For that, you need more data. You need spectroscopy. When a planet transits its star, some of the star's light passes through the planet's atmosphere on its way to Earth. Molecules in the atmosphere absorb specific wavelengths of light. By analyzing the spectrum of the star's light during the transit, astronomers can identify the chemical fingerprints of those molecules: water vapor, carbon dioxide, methane, oxygen. This technique, called transmission spectroscopy, is incredibly difficult. The signal is tiny, but it works. The James Webb Space Telescope was built to do this kind of observation, and it has already started delivering results. In September 2023, Webb observed a planet called K218b, a sub-Neptune about 120 light-years away. The planet orbits a red dwarf star in the habitable zone. It is larger than Earth, about 8.6 times Earth's mass, and it likely has a thick hydrogen-rich atmosphere. Webb's instruments detected water vapor and methane in the atmosphere. Not definitive proof of habitability, but suggestive. Water is essential for life as we know it. Methane can be produced by biological processes, though it can also come from non-biological sources. The presence of both together is interesting. It does not prove life exists there. It just means the planet has chemistry that is worth watching. Webb also detected something even more intriguing: a tentative signal of dimethyl sulfide, a molecule that on Earth is only produced by living organisms, specifically by phytoplankton in the oceans. If the detection is confirmed, if it is not a false positive or contamination from some other source, it would be one of the most significant discoveries in the history of science. Dimethyl sulfide is not a molecule you expect to find unless biology is involved. The team that published the results was cautious. They called it a tentative detection. More observations are needed. The planet is on Webb's target list for follow-up. The data will come. If the signal holds up, K218b just became the most important exoplanet we have ever found. Proxima Centauri b is closer, a lot closer. Proxima Centauri is the nearest star to the Sun, about 4.2 light-years away. It is a red dwarf, much smaller and cooler than the Sun. In 2016, astronomers announced the discovery of a planet orbiting Proxima Centauri in the habitable zone. Proxima Centauri b has a minimum mass of about 1.3 times Earth's mass. It orbits its star every 11 days, which sounds fast but is actually in the habitable zone for a red dwarf, because red dwarfs are so dim. The planet might have liquid water, it might have an atmosphere, it might be habitable, or it might be tidally locked, with one side always facing the star and the other side in permanent darkness. Red dwarf planets close to their stars tend to become tidally locked because of the strong tidal forces. A tidally locked planet is not necessarily uninhabitable, but it complicates things. The day side could be too hot. The night side could be too cold. You would need an atmosphere thick enough to transport heat from one side to the other to make it work. Proxima Centauri is also a flare star. It regularly erupts with powerful flares that blast the surrounding space with radiation. If Proxima Centauri b does not have a strong magnetic field to shield it, those flares could strip away its atmosphere over time. Earth's magnetic field protects us from solar wind and radiation. Without it, Earth would look more like Mars. Proxima Centauri b might have the same problem. We do not know. We cannot see the planet directly. It is too faint and too close to its star. We only know it exists because it tugs on the star slightly, producing a wobble we can detect with the radial velocity method. Future telescopes might be able to image it directly or study its atmosphere. Until then, Proxima Centauri b is a question mark, a very close, very interesting question mark. Then there are the moons. Gas giants are not habitable, but their moons might be. Europa, one of Jupiter's 4 large moons, has an ocean of liquid water beneath an ice shell that is probably 10 to 30 kilometers thick. The ocean is kept liquid by tidal heating, the same process that keeps Io volcanically active. Europa is not in the Sun's habitable zone. It is way too far out, but it has liquid water, it has an energy source, and observations suggest it has the right chemistry. The Galileo spacecraft, which orbited Jupiter in the late 1990s and early 2000s, detected disruptions in Jupiter's magnetic field near Europa consistent with a conductive fluid beneath the surface. Salt water. Hubble and Webb have both detected water vapor plumes erupting from Europa's surface, likely from cracks in the ice where the ocean is venting into space. Those plumes are a gift. If you can fly a spacecraft through one of those plumes and collect samples, you can analyze the ocean's chemistry without drilling through 30 kilometers of ice. NASA's Europa Clipper mission launched in October 2024. It will arrive at Jupiter in 2030 and spend several years making close flybys of Europa. One of its instruments is specifically designed to sample plume material. If Europa's ocean contains organic molecules, if it has the chemical building blocks for life, Clipper will find out. Europa is one of the best places in the solar system to search for life, and the mission has been designed with that goal explicitly in mind. Enceladus, one of Saturn's moons, is smaller than Europa but arguably even more interesting. Enceladus has geysers erupting from cracks near its south pole, spraying water vapor and ice particles into space. The Cassini spacecraft flew through those geysers multiple times during its mission and analyzed the material. The results were stunning. Water, salt, organic molecules including methane, formaldehyde, and more complex compounds. Silica particles, which on Earth form when hot water interacts with rock on the ocean floor, the kind of environment found at hydrothermal vents. Enceladus has a subsurface ocean. That ocean is in contact with a rocky core. The ocean has chemistry, and it is venting that chemistry into space where we can sample it without landing on the surface or drilling through ice. The case for life on Enceladus is not based on evidence that life actually exists there. It is based on the fact that the environment has all the ingredients life needs. Liquid water, check. Energy source in the form of tidal heating, check. Organic molecules, check. Hydrothermal activity, check. On Earth, hydrothermal vents on the ocean floor support entire ecosystems independent of sunlight. Life at those vents does not rely on photosynthesis. It relies on chemosynthesis, the process of extracting energy from chemicals in the vent fluids. If life can do that on Earth, it could do it on Enceladus. Whether it actually does is the question. Titan, Saturn's largest moon, is another strong candidate. Titan has lakes and rivers and rain, not water, methane. Titan is so cold that methane is a liquid on the surface. The atmosphere is thick, mostly nitrogen with a bit of methane, and the surface pressure is higher than Earth's. You could walk on Titan without a pressure suit. You would need oxygen and heating, but you would not explode or implode, which is more than you can say for most places in the solar system. Titan's atmosphere is full of organic chemistry. Methane breaks apart in the upper atmosphere under ultraviolet light from the sun, and the fragments recombine into more complex molecules: ethane, propane, benzene, tholins, complex organic compounds that give Titan's atmosphere its orange haze. That haze is so thick you cannot see the surface from space without using infrared or radar. The surface of Titan has hydrocarbon lakes near the poles and vast dune fields near the equator made of organic particles. The chemistry on Titan is alien. Water is frozen solid and acts like rock. Methane fills the role water plays on Earth. Life on Titan, if it exists, would have to be based on completely different chemistry than life on Earth. It would not use water as a solvent, it would use methane. Whether that is possible is an open question. Some scientists think methane-based life is plausible under Titan's conditions. Others are skeptical. The only way to know is to go look. NASA and ESA have proposed missions to Titan, including a lander and a drone that could fly through the atmosphere and explore the surface. The Dragonfly mission is currently planned for launch in 2027, with arrival in the mid-2030s. If there is something alive on Titan, Dragonfly might find it. The ingredients for life, as far as we can tell from Earth's example, are liquid water, organic molecules, and an energy source. That list is not arbitrary. It is based on the only example of life we have. Earth life uses water as a solvent. Water is a good solvent because it is liquid over a wide temperature range. It dissolves a lot of different compounds, and it is common in the universe. Organic molecules, meaning molecules with carbon backbones, are the building blocks of proteins, nucleic acids, and all the other complex molecules that make life work. Carbon is uniquely good at forming complex molecules because it can bond to itself and to other elements in flexible, stable ways, and energy is needed to drive the chemical reactions that sustain life. On Earth, that energy comes from sunlight via photosynthesis or from chemical reactions at hydrothermal vents or in the soil. Could life use a different solvent? Maybe. Ammonia and methane have been proposed as alternatives. Could life use silicon instead of carbon? Maybe, though silicon is less flexible chemically and less common in the universe. Could life exist without water? Possibly. But every time we try to imagine life without water, we end up describing something so different from Earth life that it is hard to call it life in any recognizable sense. The safest assumption, the one that guides the search for life in the solar system and beyond, is that life elsewhere will at least resemble life here in the basics: water, organic molecules, energy. If we find something that does not fit that pattern, great. That would be even more interesting. But we are not going to find it by ignoring the pattern we already know works. The search for life beyond Earth is not just about exoplanets. It is about understanding where the boundaries of habitability are. How extreme can conditions get before life becomes impossible? On Earth, life exists in environments that would kill most organisms: boiling hot springs, acidic lakes, deep underground in solid rock, the upper atmosphere, Antarctic ice. Each extreme environment supports organisms adapted to those conditions. Thermophiles thrive in temperatures above 80 degrees Celsius. Acidophiles live in acid with a pH below 3. Halophiles tolerate salt concentrations that would dehydrate most cells. Psychrophiles grow in sub-zero temperatures. Barophiles survive pressures that would crush most life. The range of conditions Earth life can tolerate is staggering, and it keeps expanding as we find life in places we previously assumed were sterile. That range matters because it defines the search space. If life can only exist in a narrow range of temperatures and pressures and chemical conditions, the number of habitable worlds is small. If life can exist in a wide range of conditions, the number of habitable worlds is large. Earth life suggests the range is wide, very wide. And if that is true, habitable environments might be common in the galaxy. Which brings us to the Fermi paradox. The paradox is simple. If planets are common, and habitable planets are common, and life is even remotely common, then intelligent life should also be common. And if intelligent life is common, the galaxy should be full of civilizations. Some of them should be millions or billions of years older than us. Those civilizations should have had time to spread across the galaxy, colonizing stars, building megastructures, leaving traces of their existence that we could detect. So where are they? Why is the night sky silent? Why have we not detected a single radio signal, a single laser pulse, a single Dyson sphere blocking out the light of a distant star? This is the Fermi paradox, named after physicist Enrico Fermi, who supposedly asked the question during a lunch conversation in 1950, "Where is everybody?" There are dozens of proposed solutions to the Fermi paradox, and none of them are satisfying. Maybe intelligent life is rare. Maybe the jump from single-celled organisms to complex multicellular life is a bottleneck that most planets never get past. Earth had single-celled life for billions of years before anything more complex evolved. Maybe that is the norm. Maybe we are one of the first. The universe is only 13.8 billion years old. Stars and planets did not start forming immediately. The first generation of stars had no heavy elements, so they could not form rocky planets. It took time for supernovae to seed the galaxy with carbon, oxygen, iron, and the other elements needed to build planets like Earth. Maybe intelligent life takes billions of years to evolve, and we are simply early. The galaxy might be full of civilizations a billion years from now. We just got here first. Or maybe intelligent civilizations do not last long. Maybe every species that reaches our level of technology eventually destroys itself. Nuclear war, climate collapse, artificial intelligence gone wrong, engineered pandemics, resource depletion. There are a lot of ways a civilization could end, and maybe all of them are hard to avoid. If the typical lifespan of a technological civilization is a few hundred or a few thousand years, the galaxy could have been full of civilizations at different times, but none of them overlap. We are shouting into the void, and by the time our signals reach another star, the civilization that might have heard us is already gone. Or maybe they are here and we just have not noticed. The zoo hypothesis suggests that advanced civilizations are deliberately avoiding contact with us, treating Earth like a nature preserve where primitive species are allowed to develop without interference. It is a nice idea. It is also unfalsifiable, which makes it useless as a scientific hypothesis. If there is no way to prove or disprove it, it does not help us understand anything. Or maybe intelligence is common, but technological civilizations are rare. Maybe most intelligent species do not develop technology. Dolphins are intelligent. Octopuses are intelligent. Neither species has built a radio telescope. Intelligence is useful for survival, but it does not automatically lead to technology. Maybe most intelligent species live in oceans or on worlds where fire is impossible, or in environments where manipulating tools is difficult. Maybe we are the weird ones, or maybe the galaxy is full of life, but most of it is not intelligent. Bacteria on Mars, microbes in the oceans of Europa and Enceladus, algae floating in the clouds of Venus. Simple life might be everywhere. Complex life might be rare. Intelligent life might be rarer still, and technological civilizations capable of sending signals across interstellar space might be so rare that there are only a handful in the galaxy at any given time. If that is true, the silence makes sense. The galaxy is huge. The odds of two technological civilizations existing close enough to detect each other at the same time are low. Or maybe we are looking in the wrong places or listening for the wrong signals. We have been searching for radio signals because we use radio, but a civilization a million years more advanced than us might have moved past radio entirely. They might be using communication methods we cannot even imagine, much less detect. Or they might not be communicating at all. Maybe once you reach a certain level of technology, there is no need to shout into space. You have everything you need at home. The search for extraterrestrial intelligence, or SETI, has been running for over 60 years. The first search, Project Ozma, was conducted by Frank Drake in 1960. He pointed a radio telescope at two nearby sun-like stars and listened for signals. He found nothing. Searches have continued ever since, growing more sophisticated and covering more stars. The Breakthrough Listen project, funded by billionaire Yuri Milner, is the most comprehensive search ever conducted. It is scanning millions of stars across multiple wavelengths, looking for anything that might be a signal. So far, nothing. A few false alarms, a few interesting candidates that turned out to be interference. But no confirmed signals. The silence continues. That silence is data. It tells us something. Either intelligent life is rare, or it does not last long, or it does not broadcast, or we are not listening correctly. Each possibility has implications. If intelligent life is rare, we need to figure out why. What makes Earth special? If it does not last long, we need to figure out the threats and how to avoid them. If it does not broadcast, we need to rethink our assumptions about what advanced civilizations do. And if we are not listening correctly, we need better tools and better strategies. The question of whether we are alone is not just a scientific question, it is a philosophical one. It shapes how we see ourselves and our place in the universe. If we are alone, if Earth is the only place where life exists, then we are cosmically unique. Every person, every species, every ecosystem is irreplaceable. The stakes are existential. If we destroy ourselves, we are not just ending our civilization, we are ending the only consciousness the universe has ever produced, at least in this corner of it. That thought is both terrifying and sobering. On the other hand, if we are not alone, if life is common and civilizations are scattered throughout the galaxy, then we are part of a larger community. We are not unique, but we are not alone either. That thought is both comforting and humbling. Right now, we do not know. The data is incomplete. The search is ongoing. And the only way to answer the question is to keep looking. Keep building better telescopes. Keep analyzing more exoplanet atmospheres. Keep listening for signals. Keep sending probes to Europa and Enceladus and Titan. The answer is out there, somewhere in the data, waiting to be found. It might be on a planet 100 light-years away with water vapor and methane and dimethyl sulfide in its atmosphere. It might be in the ocean beneath the ice on a moon orbiting Jupiter. It might be encoded in a radio signal that has been traveling through space for thousands of years and just has not reached us yet. Or it might not exist at all, and we are genuinely alone in a universe full of empty worlds. Either answer changes everything. Finding life, even microbial life on Mars or Europa, would tell us that the origin of life is not a fluke, that it happens wherever conditions allow, that the universe is fertile. Finding intelligent life would tell us that the path from chemistry to consciousness is not unique to Earth, that minds can emerge from matter in other places under other conditions, and that we are part of a much larger story. Not finding life, after searching for decades or centuries, would tell us that we are alone, that life is so improbable, so fragile, so contingent on specific conditions, that it only happened once in the observable universe. That would make us the most important thing that has ever happened in 13.8 billion years of cosmic history. We do not know which answer is true. We do not know if we will find the answer in our lifetimes, or if it will take centuries. But the search is not optional. The question is too important to ignore, And as our tools get better, as Webb and future telescopes peer deeper into the atmospheres of distant worlds, as Clipper and Dragonfly explore the moons of the outer solar system, we are finally reaching the point where the question might have an answer. Not a guess, not a statistical argument, an answer. Evidence, data, proof that we are not alone, or confirmation that we are. Both possibilities are staggering, both demand that we keep looking, because the universe has given us the tools to ask the question, and it would be a waste not to use them. The habitable zone is full of worlds. Some of them are frozen. Some of them are scorched. Some of them might be just right. And the only way to know is to point our instruments at them and listen. The search is the closest thing we have to a cosmic imperative. Look up, look out, and find out if anyone is looking back. That search is not happening in isolation. It is part of a larger effort to push the boundaries of what we know and what we can measure. And some of those boundaries are not just at the edge of the solar system or in the atmospheres of distant planets. Some of them are at the edge of physics itself, where the rules we have relied on for a century start bending in ways nobody predicted. That is where we go next. We just spent time looking for life, scanning the atmospheres of distant planets for water vapor and methane, imagining oceans beneath the ice on Europa, wondering whether something alive might be floating in the clouds of Titan or thriving around hydrothermal vents on Enceladus. The search for life is built on chemistry and conditions: liquid water, organic molecules, energy sources, places where the ingredients come together in ways that might allow biology to happen. That search assumes we understand the rules, that physics works the same way everywhere, that the forces holding atoms together here work the same way 100 light-years away or 10 billion light-years away. And for the most part, that assumption holds. The spectral lines of hydrogen look the same in a lab on Earth as they do in the light from a distant quasar. Gravity behaves predictably whether you are dropping a ball in your backyard or watching a neutron star spiral into a black hole. The rules are consistent, except there are places where the rules get strange. Phenomena so extreme, so energetic, so far outside normal experience that they push right up against the boundaries of what our theories can explain. And in some cases, they push past those boundaries entirely. Cosmic rays that carry more energy than anything we can produce in a particle accelerator. Neutrinos that pass through the entire Earth without slowing down. Explosions so powerful they outshine entire galaxies for a few seconds. Ripples in space-time itself, caused by colliding black holes, and threading through all of it, two massive, invisible components that make up most of the universe and that we do not understand at all. Dark matter, dark energy, the stuff we cannot see, cannot touch, and can barely detect, but that apparently accounts for 95% of everything that exists. This is where physics breaks, or more accurately, this is where our current understanding of physics hits a wall and we are forced to admit that the map we have been using is incomplete. The territory is bigger and stranger than the map suggests, and figuring out what is missing, what new rules we need to add or what old rules we need to revise, is one of the biggest challenges in science right now. So let's talk about the edge, the frontier, the places where the universe does things we did not think were possible and forces us to reconsider what we thought we knew. Start with cosmic rays because they have been hitting Earth since long before anyone knew what they were. Cosmic rays are not rays. The name is a historical accident. When they were first detected in the early 1900s, scientists thought they were some kind of electromagnetic radiation, like X-rays or gamma rays. Turns out they are particles, mostly protons. Some atomic nuclei, helium, carbon, iron, heavier elements, high-energy particles traveling through space at speeds close to the speed of light. They hit Earth's atmosphere constantly, thousands of them every second, colliding with air molecules and creating cascades of secondary particles that rain down toward the surface. Most of them are absorbed by the atmosphere before they reach the ground, which is fortunate because high-energy particles slamming into living tissue tend to damage DNA. The atmosphere acts as a shield. Stand at sea level and you are relatively safe. Fly in an airplane and your radiation dose goes up because you are higher and the shielding is thinner. Astronauts on the International Space Station get even more exposure. Leave Earth's magnetosphere entirely, head out toward Mars or beyond, and cosmic rays become a serious problem. Long-duration space missions will need better shielding if we want astronauts to survive the trip without accumulating dangerous levels of radiation damage. The interesting thing about cosmic rays is not that they exist. It is how much energy some of them carry. Most cosmic rays are low energy by particle physics standards. A few million electron volts, maybe a few billion. That is energetic enough to be dangerous to biological tissue but not particularly impressive compared to what particle accelerators can do. The Large Hadron Collider at CERN accelerates protons to about 13 trillion electron volts. That is a lot. A cosmic ray with that much energy would not make headlines, but every so often a cosmic ray hits Earth's atmosphere with energy far beyond anything the LHC can produce. The highest energy cosmic ray ever detected, observed in 1991 by the Fly's Eye detector in Utah, had an energy of about 300 million trillion electron volts, 3 times 10 to the 20th electron volts. That is roughly the kinetic energy of a baseball thrown at 90 miles per hour, except all that energy is packed into a single subatomic particle, one proton or nucleus, moving so fast that relativistic effects dominate, and its mass, from the perspective of a stationary observer, is enormous. Where do particles like that come from? Nobody knows for sure. The leading candidates are supernova remnants, active galactic nuclei, and gamma-ray bursts. When a massive star explodes, the shockwave accelerates particles to extreme energies. When a supermassive black hole at the center of a galaxy is feeding and launching jets of material at relativistic speeds, particles in those jets can reach incredible energies. Gamma-ray bursts, the most powerful explosions in the universe, could accelerate particles even further. But the math is tricky. Accelerating a particle to 300 million trillion electron volts requires an acceleration region the size of a galaxy or larger, or an environment so extreme that the physics gets messy. We can model it, we can simulate it, but we cannot point to a specific object and say with certainty that is where the ultra-high energy cosmic rays come from. The universe is producing particles with energies we cannot replicate in a lab, and we are still figuring out how. Then there are neutrinos. Neutrinos are particles so reluctant to interact with anything that they make ghosts look gregarious. A neutrino can pass through a light year of solid lead and probably not hit a single atom. They are produced in nuclear reactions, particularly fusion reactions in stars and fission reactions in nuclear reactors. The Sun produces neutrinos by the trillions every second. Right now, as you are reading this or listening to this, billions of neutrinos from the Sun are passing through your body. They pass through the floor beneath you, through the Earth, and out the other side without slowing down. You do not notice, they do not interact. They are there, they are real, they carry energy and momentum, but from your perspective, they might as well not exist. Detecting neutrinos is an exercise in patience and scale. You need a huge detector because even though trillions of neutrinos are passing through it every second, only a tiny fraction will interact with anything, and you need to put that detector somewhere shielded from other particles like cosmic rays that could produce false signals. Most neutrino detectors are built deep underground or under ice. The Super Kamiokande detector in Japan sits a kilometer underground in a zinc mine. It is a giant tank containing 50,000 tons of ultra-pure water, lined with photomultiplier tubes that watch for flashes of light. When a neutrino, on rare occasion, does interact with a water molecule, it produces a charged particle that moves through the water faster than light moves through water. That generates a cone of light called Cherenkov radiation, and the photomultiplier tubes detect it. From the pattern of light, physicists can reconstruct the direction and energy of the neutrino. Super Kamiokande was built to study neutrinos from the Sun and from cosmic rays hitting the atmosphere. In 1998, it provided the first strong evidence that neutrinos have mass. That might not sound like a big deal. Everything has mass, right? Except the original formulation of the Standard Model of Particle Physics, the theory that describes all known particles and 3 of the 4 fundamental forces, assumed neutrinos were massless. They were supposed to zip around at the speed of light like photons, but experiments showed that neutrinos oscillate, they change flavor. There are 3 types of neutrinos: electron neutrinos, muon neutrinos, and tau neutrinos, and a neutrino produced as one type can turn into another type as it travels. That transformation is only possible if neutrinos have mass. The oscillation was detected, the mass was confirmed, and the Standard Model, which had been extraordinarily successful at predicting and explaining particle behavior for decades, needed an update. Neutrino mass is a crack in the foundation, not a fatal crack. The model can be extended to accommodate neutrino mass, but the fact that it was not included originally means there is something missing. Some mechanism that gives neutrinos mass. And whatever that mechanism is, it is not part of the Standard Model as it was written. Neutrinos are also useful as astronomical messengers. When a star collapses and explodes in a supernova, most of the energy is carried away by neutrinos, not light. The core collapse happens fast, less than a second, and the temperature and density spike so high that neutrinos are produced in staggering numbers. About 99% of the energy released in a supernova leaves as neutrinos. Only about 1% comes out as light, the visible explosion we see when the shockwave reaches the surface and blows the outer layers apart. In 1987, a supernova exploded in the Large Magellanic Cloud, a small galaxy orbiting the Milky Way about 160,000 light-years away. Supernova 1987A was the closest supernova visible to the naked eye since 1604, and it was also the first time neutrino detectors caught neutrinos from a supernova. A few hours before the light from the explosion reached Earth, detectors in Japan and the United States picked up a burst of neutrinos, 19 neutrinos total across both detectors. That does not sound like much, but it confirmed the theory. Core collapse produces neutrinos, lots of them, and they arrive before the light because they escape the collapsing core immediately, while the light has to fight its way out through the rest of the star. Neutrino astronomy has grown since then. The ice cube detector at the South Pole is a cubic kilometer of Antarctic ice instrumented with thousands of sensors looking for Cherenkov light from neutrinos. IceCube is not looking for solar neutrinos or supernova neutrinos. It is looking for high-energy neutrinos from distant astrophysical sources, active galactic nuclei, gamma-ray bursts, blazars, any object capable of accelerating particles to extreme energies will also produce neutrinos, and those neutrinos travel in straight lines through the universe unaffected by magnetic fields or intervening matter. A photon from a distant galaxy might scatter or get absorbed along the way. A neutrino will not. If you detect a neutrino and you can trace its direction back to the source, you are seeing straight into the engine that produced it. Gamma-ray bursts are the most powerful explosions known. They make supernovae look tame. A typical gamma-ray burst releases as much energy in a few seconds as the Sun will emit over its entire 10 billion-year lifetime. Some bursts are even more powerful. The energy comes out in a narrow jet, a beam of gamma rays and particles blasted out at close to the speed of light. If the jet happens to be pointing at Earth, we see the burst. If it is pointing somewhere else, we see nothing. That directionality is important because it means the bursts we detect are only a fraction of the total number happening in the universe. Every burst we see represents dozens or hundreds of bursts happening in other directions that we miss entirely. There are two main types of gamma-ray bursts: short bursts, lasting less than 2 seconds, and long bursts, lasting more than 2 seconds and sometimes stretching to several minutes. The distinction is not arbitrary. The two types have different causes. Short bursts are usually produced by the merger of two neutron stars, or a neutron star and a black hole. When two neutron stars spiral together, they collide and release an enormous amount of energy. Some of that energy goes into gravitational waves, which we will get to in a moment. Some of it goes into neutrinos, and some of it goes into a jet of gamma rays. Long bursts are usually associated with the collapse of a massive star, a hypernova, where the core collapses directly into a black hole and the infalling matter forms an accretion disk that launches a jet perpendicular to the disk. The jet punches through the outer layers of the star and escapes into space, carrying gamma rays and high-energy particles with it. The physics of gamma-ray bursts is messy. The jets are moving at relativistic speeds, which means you have to account for time dilation, Doppler shifts, and all the strange effects that happen when things approach the speed of light. The gamma rays we detect are the result of particles in the jet colliding with each other or with photons and producing high-energy radiation through processes like synchrotron radiation and inverse Compton scattering. Modeling all of that requires simulations, and even the best simulations are only approximations because the conditions inside a gamma-ray burst jet are so extreme that some of the physics is still uncertain. Gamma-ray bursts are also useful as probes of the early universe. Because they are so bright, they can be detected from enormous distances. Some of the bursts we have observed come from galaxies more than 13 billion light-years away, meaning we are seeing them as they were less than a billion years after the Big Bang. By studying the light from those bursts as it passes through intervening gas clouds, astronomers can learn about the composition of the early universe, the distribution of heavy elements, and the process by which the first galaxies enriched their surroundings with metals. Now, gravitational waves. Einstein predicted them in 1916, almost immediately after he finished developing general relativity. If space-time is a fabric that can be curved by mass and energy, then accelerating masses should produce ripples in that fabric, waves that propagate outward at the speed of light. For decades, gravitational waves were a theoretical curiosity. Nobody had detected them directly, and most physicists assumed they were too weak to ever measure. Then, in 1974, astronomers discovered a binary pulsar system, two neutron stars orbiting each other, and they noticed that the orbit was decaying. The two stars were spiraling closer together, losing energy at exactly the rate general relativity predicted they would if they were emitting gravitational waves. That was indirect evidence. The waves themselves had not been detected, but the system was behaving as if they existed. Joseph Taylor and Russell Hulse won the Nobel Prize in 1993 for that discovery. Direct detection came in 2015. The Laser Interferometer Gravitational Wave Observatory, LIGO, consists of two detectors, one in Washington and one in Louisiana. Each detector is an L-shaped instrument with arms 4 kilometers long. Lasers bounce back and forth along the arms, and if a gravitational wave passes through, it stretches space in one direction and compresses it in the other direction. The effect is tiny. The distance change is smaller than the diameter of a proton. But LIGO is sensitive enough to measure it. On September 14, 2015, both detectors picked up a signal, a chirp, a rapid increase in frequency lasting a fraction of a second. The waveform matched the prediction for two black holes spiraling together and merging. The masses were about 29 and 36 times the mass of the Sun. The final merged black hole was about 62 solar masses. The missing 3 solar masses were converted into energy and radiated away as gravitational waves. The energy released in that fraction of a second was more than the combined light output of every star in the observable universe. For a brief moment, the collision was the most powerful event happening anywhere in the cosmos. LIGO has detected dozens of gravitational wave events since then. Most of them are black hole mergers. A few are neutron star mergers. In 2017, LIGO and its European counterpart Virgo detected a neutron star merger, and this time telescopes around the world were able to observe the event in light as well. Gamma rays, X-rays, visible light, infrared, radio waves. Every part of the spectrum lit up as the neutron stars collided, merged, and produced a kilonova, a burst of heavy elements forged in the extreme conditions of the merger and flung into space. That single event confirmed that neutron star mergers are the source of much of the gold, platinum, and other heavy elements in the universe. Every gold ring, every platinum catalyst, every rare earth element in your phone. A significant fraction of it was made in collisions like that one. The atoms were forged in the collision, scattered into space, and billions of years later incorporated into the cloud of gas that collapsed to form the Sun and the planets. Gravitational wave astronomy is still in its infancy, but it has already opened a new window on the universe. For centuries, astronomy was limited to light. We could only see things that emitted or reflected electromagnetic radiation. Now we can detect events that produce almost no light at all. Black hole mergers happen in the dark. If it were not for gravitational waves, we would have no way to observe them. Neutrinos and gravitational waves are messengers that do not interact with matter the way light does. They carry information that light cannot. And combining observations across all these channels, electromagnetic radiation, neutrinos, gravitational waves, gives us a much richer picture of what is happening in the most extreme environments in the universe, which brings us to the big problem, the missing mass problem, the invisible universe. In the 1930s, astronomer Fritz Zwicky was studying the Coma cluster, a large cluster of galaxies about 300 million light-years away. He measured the velocities of galaxies in the cluster and used those velocities to estimate the total mass. The galaxies were moving fast, too fast to be held together by the gravity of the visible matter alone. Zwicky concluded that there must be a lot of unseen matter in the cluster, matter that does not emit light but does exert gravitational force. He called it dark matter. Nobody took him seriously at the time. Zwicky had a reputation for being difficult, and his idea sounded too strange. The notion that most of the matter in the universe could be invisible did not fit with the models of the day. The evidence kept piling up. In the 1970s, astronomer Vera Rubin measured the rotation curves of spiral galaxies. A rotation curve is a graph showing how fast stars are moving at different distances from the galactic center. Based on the distribution of visible matter, stars farther from the center should move slower because they are feeling less gravitational pull. That is how the planets in the solar system behave. Mercury orbits faster than Earth. Earth orbits faster than Mars. The farther out you go, the slower the orbit. But galaxies do not behave that way. The stars at the edge of a galaxy are moving just as fast as the stars closer in. The rotation curves are flat. The only way to explain that is to add a lot of invisible mass, a halo of dark matter surrounding the galaxy, extending far beyond the visible disk, providing the extra gravity needed to keep the outer stars moving as fast as they are. Gravitational lensing provides more evidence. When light from a distant galaxy passes near a massive foreground object, like a galaxy cluster, the gravity of the foreground object bends the light, creating distorted images of the background galaxy. By measuring the amount of distortion, astronomers can calculate the mass of the foreground object, and every time they do this, the mass comes out much higher than the visible matter can account for. The lensing effect is too strong. There is more mass there than we can see. Dark matter, the cosmic microwave background, the afterglow of the Big Bang, also shows the fingerprints of dark matter. The tiny temperature fluctuations in the CMB, measured in exquisite detail by satellites like WMAP and Planck, encode information about the density and composition of the universe when it was only 380,000 years old. The pattern of fluctuations matches the predictions of a universe where about 27% of the mass energy is dark matter and about 68% is dark energy. Normal matter, the stuff we are made of, makes up less than 5%. We are the minority. The universe is mostly stuff we cannot see, so what is dark matter? The honest answer is we do not know. The leading candidate for decades has been WIMPs, weakly interacting massive particles. These are hypothetical particles that interact only through gravity and possibly the weak nuclear force. They would not emit or absorb light, which explains why they are invisible. They would pass through normal matter with almost no interaction, which explains why we have not detected them directly. And if they have the right mass and interaction strength, they would have been produced in large quantities in the early universe and would still be around today, making up the dark matter halos we infer from observations. The problem is that, despite decades of searching, nobody has detected a WIMP. Experiments like the Large Hadron Collider have looked for them. Underground detectors designed to catch WIMPs passing through Earth have looked for them. Nothing. The searches continue, but the lack of a detection is starting to make people nervous. Other candidates include axions, hypothetical particles originally proposed to solve a different problem in particle physics, but which could also serve as dark matter if they exist in the right quantities. Sterile neutrinos, a fourth type of neutrino that does not interact through the weak force and would be even harder to detect than ordinary neutrinos. Primordial black holes formed in the first moments after the Big Bang that could be drifting through the universe undetected. Each candidate has its strengths and weaknesses. Each has experiments designed to search for it. None have been confirmed. The alternative to dark matter is to modify gravity. If the equations of general relativity are not quite right on large scales, maybe you can explain the observations without adding invisible matter. Modified Newtonian dynamics, or MAND, is one such proposal. It tweaks the equations so that gravity behaves differently in regions of very low acceleration, like the outer edges of galaxies. Menuini can explain galaxy rotation curves reasonably well, but it struggles with galaxy clusters and gravitational lensing, and it does not explain the cosmic microwave background observations at all. Most physicists think dark matter is the more likely explanation, but until we detect the particle directly, there is room for doubt. Dark energy is an even bigger mystery. In the late 1990s, two teams of astronomers were using Type 1a supernovae as standard candles to measure the expansion history of the universe. Type 1a supernovae are useful because they all explode with roughly the same peak brightness. Measure how bright they appear, and you can calculate how far away they are. Measure their redshift, and you can calculate how fast they are moving away from us. Combine the two, and you can figure out how the expansion rate has changed over time. The expectation was that the expansion should be slowing down. Gravity pulls everything together, so the expansion should decelerate. Both teams found the opposite. The expansion is accelerating. Distant supernovae are dimmer than they should be, which means they are farther away than expected, which means space has expanded more than it should have if the expansion were slowing down. The only way to explain accelerating expansion is to add a new component to the universe, something with negative pressure that pushes space apart. That something is dark energy, and it makes up about 68% of the total energy density of the universe. Dark energy does not clump like matter. It does not form structures. It is spread uniformly through space, and its effect is to push things apart on the largest scales. Within galaxy clusters, gravity dominates, and dark energy is negligible. But on scales of hundreds of millions of light-years or more, dark energy dominates, driving the accelerated expansion. The leading explanation for dark energy is the cosmological constant, a term Einstein originally added to his equations of general relativity to make the universe static. When Hubble discovered the universe was expanding, Einstein supposedly called the cosmological constant his biggest blunder and removed it. Turns out it might have been right all along. A cosmological constant corresponds to a constant energy density filling all of space, an energy inherent to the vacuum itself. Quantum field theory predicts that the vacuum should have energy, but the predicted value is wildly wrong. The theoretical estimate is about 120 orders of magnitude larger than the observed value. That is not a typo. 120 orders of magnitude. It is one of the worst predictions in the history of physics. Something is cancelling most of the vacuum energy, leaving only a tiny residual amount that we observe as dark energy. What is doing the cancelling? Nobody knows. Other proposals include quintessence, a dynamic field that changes over time, or modifications to general relativity on very large scales. Each idea has challenges, each requires new physics, and each would have profound implications for the fate of the universe. If dark energy is constant, the universe will expand forever. Galaxies will drift apart, and eventually the night sky will go dark as everything moves beyond the cosmic horizon. If dark energy gets stronger, the expansion will accelerate faster and faster until it tears galaxies apart, then stars, then planets, then atoms in a scenario called the Big Rip. If dark energy weakens or reverses, the expansion could stop and reverse, leading to a big crunch where everything collapses back into a single point. Right now, all evidence points to constant or slowly changing dark energy, which means eternal expansion, but the data is still being refined. The universe is doing things we do not fully understand, accelerating particles to energies we cannot replicate, producing explosions that outshine galaxies, warping space-time enough to create detectable ripples, and filling most of its volume with matter and energy we cannot see and barely know how to look for. That is the frontier, the place where our maps run out and the signs start saying, "Here be dragons." Except in this case, the dragons are real, and they are made of dark matter and powered by dark energy, and they are everywhere. We live in a universe that is mostly invisible, mostly mysterious, and mostly unknown. The parts we can see, the stars and galaxies and planets, are just the tip of a much larger structure. And understanding that structure, filling in the blank spaces on the map, is one of the great challenges of modern science. It is not an abstract problem. It is not just about satisfying curiosity. The missing 95% of the universe is holding everything together and pulling everything apart at the same time. It is the reason galaxies exist, the reason the universe has the structure it does, the reason we are here at all. And we do not know what it is. That gap, that enormous hole in our understanding, is where the next breakthroughs will come. New detectors, new telescopes, new experiments, new theories. Something is going to give. Some piece of data is going to fall into place, and when it does, the picture will shift. Maybe dark matter will be detected, maybe a new particle will show up at a collider, maybe gravitational wave observations will reveal something nobody predicted, or maybe the answer is not a new particle or a new force, but a completely different way of thinking about space and time and gravity that makes the current confusion look obvious in hindsight. That has happened before. It will happen again, and when it does, the frontier will move, the map will expand, and the universe will get stranger and more interesting than it already is. Because if there is one lesson from the last century of physics, it is that every time we think we have figured something out, every time we think the picture is complete, the universe finds a way to surprise us. The edge of understanding is not a wall, it is a horizon. And beyond that horizon there is more, always more, which is where we go next. We just spent time at the edge of physics, dark matter halos surrounding galaxies we cannot see, dark energy tearing space apart, cosmic rays carrying more energy than anything we can build, gravitational waves rippling through space-time from black holes colliding billions of light-years away, neutrinos that pass through the Earth like it is not even there. All of it strange. All of it pushing against the boundaries of what our theories can explain, and all of it, every weird phenomenon, every broken prediction, every particle we cannot find, and every force we cannot name, is happening inside the observable universe, inside the bubble, the 93 billion light-year sphere of everything we can in principle ever see. That is the playing field. That is the arena where physics operates, and where our instruments can gather data, and where our models can be tested against reality. But the observable universe is not the universe, it is just the part we have access to. The part where light has had enough time since the Big Bang to reach us. Beyond that boundary, beyond the cosmic horizon, there is more. There has to be. Space does not just stop at the edge of our vision. The Big Bang did not happen in one place and leave the rest of the universe empty. It happened everywhere. Every point in space was once the same point, and when expansion began, it began uniformly, which means the regions beyond what we can see are probably not fundamentally different from the regions we can see. Same physics, same forces, same types of matter and energy, more galaxies, more stars, more planets, more of the same, stretching outward into a volume we can model but never observe. That assumes the cosmological principle holds. The cosmological principle is one of those ideas that sounds obvious until you think about it for more than a few seconds. It says the universe, on large enough scales, is homogeneous and isotropic. Homogeneous means it looks the same everywhere. Isotropic means it looks the same in every direction. No special locations, no preferred directions. You are not at the center. Nobody is at the center. There is no center. Every observer, no matter where they are in the universe, sees roughly the same large-scale structure, the same density of galaxies, the same expansion rate, the same cosmic microwave background temperature. The cosmological principle is a statement about symmetry, an assumption that the universe does not care where you are or which way you are facing, and the evidence so far supports it. Maps of the cosmic microwave background show that the temperature is uniform to within 1 part in 100,000 across the entire sky. That uniformity tells us the early universe was smooth, not perfectly smooth, but close, Surveys of galaxies show that the distribution, while clumpy on small scales with clusters and filaments and voids, averages out to a uniform density on scales of a few 100 million light-years or larger. No matter which direction you look, you see roughly the same number of galaxies per unit volume once you smooth over the local structure. That is isotropy, and observations of distant supernovae, galaxy redshifts, and the large-scale structure all point to the same conclusion. The universe, at least the part we can see, is statistically uniform. If the cosmological principle holds, and there is no reason to think it does not, then the regions beyond the observable universe are probably similar to the regions inside it. More galaxies, more clusters, more voids, the same cosmic web, just farther out. You could, in principle, get in a spaceship, travel beyond the current horizon, and find yourself surrounded by galaxies that look basically like the ones near Earth. Different galaxies, obviously, different stars, different planets, but the same kinds of objects governed by the same laws of physics. The universe does not change its rules just because you have moved outside the bubble we happen to live in. That picture is comforting in its simplicity. The universe is big, maybe infinite, but it is the same kind of big everywhere. No edges, no walls, no places where gravity works differently or where stars are made of something other than hydrogen and helium. Just more space, stretching on forever, or at least much farther than we will ever be able to see. For a long time, that was the consensus view. The universe is what you see scaled up. Extrapolate outward, and you get more of the same. Then cosmology got complicated. Inflation theory, proposed in the early 1980s, solved a bunch of problems with the standard Big Bang model. It explained why the universe is so flat, why it is so uniform, why we do not see magnetic monopoles or other exotic relics from the early universe that should exist if certain high-energy physics theories are correct. Inflation says that in the first fraction of a second after the Big Bang, the universe underwent a period of exponentially fast expansion. Space doubled in size over and over again in an unimaginably short time, smoothing out any initial irregularities and stretching the observable universe to a size vastly larger than it would have been without inflation. The observable universe today is a tiny patch of a much larger inflated region, and that larger region is so smooth and so uniform that we cannot tell from inside it that inflation ever happened. We just see the aftermath, a flat, uniform cosmos. Inflation works, it explains the data. It makes predictions that have been confirmed by observations of the cosmic microwave background. But inflation also comes with baggage. Once you introduce a mechanism that can inflate space exponentially, it is hard to turn it off everywhere at once. The original inflationary models assumed inflation started, ran for a brief period, and then stopped, leaving behind a universe that has been expanding normally ever since. But some versions of inflation, called eternal inflation, suggest that inflation never fully stops. It ends in some regions like ours where inflation stopped and normal expansion took over and galaxies formed. But in other regions, inflation keeps going. And in those regions, new pockets of space eventually stop inflating and form their own separate observable universes. Each pocket is causally disconnected from the others because the inflating regions between them are expanding faster than light can cross them. You end up with a multiverse, a vast, possibly infinite collection of bubble universes, each with its own Big Bang, its own laws of physics possibly, or at least its own values for the fundamental constants and its own history. This is where things get speculative. The multiverse is not a single well-defined idea. It is a category that includes several different proposals, some of which have nothing to do with inflation. The simplest version, sometimes called the quilted multiverse, is just the idea that if space is infinite and the number of possible configurations of matter is finite, then every possible arrangement must repeat somewhere. An infinite universe with a finite number of configurations means there are an infinite number of regions that look exactly like ours, exact copies of Earth, exact copies of you. That follows logically from infinity plus finite possibilities. It is also completely untestable. We cannot observe those distant regions. We cannot compare them to ours. We just have to accept that if the universe is infinite and the cosmological principle holds, then somewhere far beyond the horizon there is another version of you reading or listening to this exact script. The inflationary multiverse is different. It is not about infinite repetition. It is about separate bubbles, each of which could have different physical properties. In some models, the constants of nature, the strength of gravity, the mass of the electron, the charge of the proton, are not fixed. They are set by a field that settles into different values in different bubbles. Our bubble has the values we measure. Another bubble might have a stronger gravitational constant, leading to a universe where stars burn out faster and galaxies never form. Another bubble might have a weaker electromagnetic force, leading to atoms that do not hold together the way ours do. Most bubbles would be lifeless. Most would not have stable structures. The fact that we find ourselves in a bubble where the constants allow for complexity and life is not surprising. We could not exist in a bubble where the constants were wildly different. This is the anthropic principle. The universe looks fine-tuned for life, not because it was designed, but because we are observing it from inside one of the rare bubbles where observers can exist. The anthropic principle makes some physicists deeply uncomfortable. It feels like giving up. It says we cannot predict the constants of nature because they are environmental accidents determined by where you happen to live in the multiverse, rather than by some deeper underlying theory. If that is true, then a huge chunk of physics is beyond the reach of prediction. We can measure the constants in our universe, but we can never derive them from first principles because there are no first principles, just a landscape of possibilities and random selection. Other physicists are fine with it. They point out that the multiverse, if it exists, is a consequence of inflation, not an assumption. We did not invent the multiverse because we wanted to explain fine-tuning. It fell out of the equations, and if the equations predict it, we should take it seriously, even if it is unobservable. That is the key problem, unobservable. By definition, other bubbles in the multiverse are beyond our cosmic horizon. They are regions of space that are receding from us faster than light, carried away by the expansion of the inflating regions between us and them. No signal from another bubble can ever reach us. No particle, no photon, no gravitational wave. We are causally disconnected, which means the multiverse, as an idea, sits in a strange place. It is a prediction of a scientific theory, inflation, but it is not itself testable in the way most scientific predictions are. You cannot point a telescope at another universe. You cannot run an experiment that confirms or rules out the existence of other bubbles. The best you can do is test inflation itself and see if the version of inflation that predicts eternal inflation is the one that fits the data. But even that is tricky because most versions of inflation make similar predictions for the observable universe. The differences show up in the unobservable parts. Some theorists have tried to find indirect evidence for the multiverse. If our bubble collided with another bubble at some point in the past, the collision might have left a mark on the cosmic microwave background. A circular pattern of slightly higher or lower temperature in one part of the sky. Searches for those patterns have found nothing conclusive. A few candidates, but nothing that could not also be explained by random fluctuations. Other proposals involve looking for anomalies in the large-scale structure of the universe that might indicate we are near the edge of a bubble, or that our bubble has unusual properties compared to typical bubbles. Again, nothing definitive. The multiverse remains a hypothesis without direct observational support. Then there are other kinds of multiverses. The many worlds interpretation of quantum mechanics, for instance, proposes that every time a quantum measurement happens, the universe splits into multiple branches, one for each possible outcome. In one branch, the particle goes left. In another branch, it goes right. Both branches are real. Both exist. You just happen to be in one of them. The many worlds interpretation solves the measurement problem in quantum mechanics, the question of why we see definite outcomes when quantum mechanics predicts probabilities. The answer is we see definite outcomes because we are inside one branch, but all the other branches exist too, carrying versions of us that saw different outcomes. Many worlds is popular among some physicists because it avoids the need for wave function collapse, a concept that has always been a bit mysterious, but it is also untestable. You cannot communicate with the other branches. You cannot measure them. You just have to accept that they are there. The holographic principle is another strange idea that sometimes gets lumped into multiverse discussions, though it is really about the structure of spacetime rather than the existence of other universes. The holographic principle, which emerged from studies of black hole thermodynamics, suggests that all the information contained in a volume of space can be encoded on the boundary of that volume. A three-dimensional region can be fully described by a two-dimensional surface surrounding it. It is as if the universe is a hologram, a projection of information from a lower dimensional boundary. This idea has been developed into a more precise framework called the AD-SCFT correspondence, which relates certain types of gravitational theories in higher dimensional spaces to quantum field theories on lower dimensional boundaries. The math works. The correspondence has been tested in specific cases and holds up. Whether it applies to the real universe is still an open question. But if it does, it would mean the three-dimensional space we experience is in some sense not fundamental. The real physics is happening on a two-dimensional surface, and we are living inside the projection. All of these ideas, the inflationary multiverse, the many worlds interpretation, the holographic principle, sit at the edge of what science can address. They are consequences of theories that explain observable phenomena, but they themselves make predictions about things we cannot observe. That puts them in a difficult position. Are they science or philosophy? Are they testable hypotheses or speculative extensions of successful theories into untestable territory? The line is not always clear. Science has always involved some degree of speculation. You propose an idea, you test it, and if it survives the tests, you take it seriously. But when the idea makes predictions that are by definition beyond the reach of any test, the usual process breaks down. You are left with internal consistency and explanatory power, which are useful, but not the same as empirical confirmation. And yet, dismissing these ideas outright feels premature. Inflation is a good example. When it was first proposed, many physicists were skeptical. It seemed too convenient. It solved too many problems at once. It required a new field, the inflaton, that nobody had detected. But over time, as observations got better and the predictions of inflation were confirmed, skepticism faded. Inflation is now part of the standard cosmological model, not proven beyond all doubt, but widely accepted because it works. The multiverse might follow a similar path, or it might not. The key difference is that inflation makes predictions about the observable universe. The cosmic microwave background should be flat. It should have a specific pattern of fluctuations. Those predictions were tested and confirmed. The multiverse, at least the versions that involve causally disconnected regions, does not make predictions about our universe that differ from what you would predict without a multiverse. It is a consequence of the theory, but not a testable consequence. So where does that leave us? Standing at the edge of the observable universe, looking outward and asking what lies beyond. The most conservative answer is more of the same. More galaxies, more stars, more planets. The universe continues, governed by the same physics, stretching outward far beyond what we can see. If space is infinite, it stretches forever. If space is finite but unbounded, like the surface of a sphere but in higher dimensions, it curves back on itself and has no edge. Either way, there is no wall. No place where you hit the end and find a sign that says you are now leaving the universe. The observable universe is just the region we have access to, defined by the speed of light and the age of the universe. Beyond that region, the universe continues. We cannot see it, we cannot visit it, but it is there. The speculative answer is that the universe is far stranger than more of the same. That our observable universe is one bubble in a vast multiverse. That the constants of nature we measure are local accidents. That there are other regions, other bubbles, where physics works differently and structures we take for granted do not exist. Or that quantum mechanics is splitting the universe into branches every moment, creating an infinite tree of parallel histories. Or that space-time itself is a hologram, a projection from a boundary we cannot see. All of these ideas are internally consistent. All of them solve real problems in physics, and all of them extend beyond what we can observe. The philosophical impact of all this is hard to overstate. For most of human history, the universe was small. Earth at the center, the sky a dome, the stars lights attached to the firmament. Then Copernicus moved Earth out of the center. Then Hubble showed that the Milky Way was one galaxy among billions. Then we learned that billions is an underestimate and the real number might be in the trillions. Each step made the universe bigger and made humanity's place in it smaller. We went from the center of creation to inhabitants of a planet orbiting an average star in a galaxy that is one of trillions. And now, maybe our entire observable universe is just one bubble in an infinite multiverse where most bubbles are empty or hostile or governed by different laws. The scale is overwhelming, the implications are humbling, and the uncertainty is maddening. Because the thing is, we might never know. The observable universe is expanding. Dark energy is driving that expansion to accelerate. Galaxies that are currently visible will, over billions of years, drift beyond the cosmic horizon. The night sky will get darker, emptier. Future civilizations, if they exist and if they arise billions of years from now, will look up and see almost nothing. A few nearby galaxies in their local group, held together by gravity, and beyond that, darkness. The cosmic microwave background will have redshifted into invisibility. The evidence for the Big Bang will be gone. They will have no way to know that the universe was once full of galaxies, that there was a hot, dense beginning, that space has been expanding for billions of years. They will be trapped in an island of light surrounded by a void that gives them no information about the larger cosmos. They might assume their local group is the entire universe. They might never discover cosmology the way we have because the data they need will no longer be accessible. We are lucky. We live at a time when the universe is old enough to be interesting but young enough that we can still see the evidence. The cosmic microwave background is still visible. Distant galaxies are still detectable. The expansion history is still written in the light from supernovae and quasars. We have a window, a brief period, cosmologically speaking, where the universe is revealing its history to anyone who looks carefully. That window will not stay open forever. Eventually, the information will be lost, redshifted out of reach, and future observers will have a much harder time piecing together the story, which makes the work happening now, the telescopes being built, the missions being planned, the data being analyzed, all the more important. The James Webb Space Telescope is looking at the earliest galaxies, pushing the observational frontier back toward the first few 100 million years after the Big Bang. Gravitational wave observatories like LIGO and Virgo are detecting collisions of black holes and neutron stars, events that were invisible to all previous generations of astronomers. Neutrino detectors are catching particles from supernovae and distant cosmic accelerators. All of these instruments are extending the reach of observation, not beyond the cosmic horizon that is still impossible, but deeper into the observable universe and into regimes of physics that were previously inaccessible. Future missions will go further. The Nancy Grace Roman Space Telescope, set to launch in the mid-2020s, will survey large areas of the sky in infrared, looking for distant galaxies and studying dark energy. The Einstein Telescope and Cosmic Explorer, next-generation gravitational wave detectors, will be sensitive enough to detect black hole mergers from the very early universe, possibly even from the era before the first stars formed. Those detections would give us a direct window into the Dark Ages, the period between the cosmic microwave background and the formation of the first galaxies, a time we currently know almost nothing about. Space-based interferometers like LISA, the Laser Interferometer Space Antenna, will detect gravitational waves at lower frequencies than ground-based detectors can reach, opening up new classes of sources, including supermassive black hole mergers. Each new instrument, each new survey, each new detection adds pieces to the map. The map will never be complete. The observable universe is too large and too complex for any single mission or any single generation of astronomers to fully catalogue. But the map is getting better. The blank spaces are shrinking, the details are coming into focus, and occasionally something shows up that does not fit. An anomaly, a signal that should not be there, a measurement that contradicts the model. Those are the moments that matter because they are the cracks where new physics might be hiding. We are living in a golden age of cosmology, a time when the tools are finally good enough to test ideas that were pure speculation a generation ago. Dark matter, dark energy, gravitational waves, the cosmic microwave background, the formation of the first galaxies, the distribution of large-scale structure, all of it is now observable, measurable. The universe is not holding back. It is showing us what it is made of and how it got here. The challenge is interpreting the data, building models that fit, testing those models against new observations, refining the picture. That process is slow, it is painstaking, it is frustrating when the data contradicts expectations, but it works. It is how we went from thinking the Milky Way was the entire universe to knowing that the observable universe contains trillions of galaxies. It is how we discovered the Big Bang, dark matter, dark energy, black holes, gravitational waves. Every major discovery in cosmology over the last century has come from careful observation combined with bold theoretical ideas. That combination is not going away. If anything, it is accelerating, and maybe, just maybe, one of those future observations will tell us something about what lies beyond. Not by seeing past the horizon, that is impossible, but by finding evidence in what we can see that constrains what we cannot. Patterns in the cosmic microwave background that hint at collisions with other bubbles. Anomalies in the distribution of galaxies that suggest our observable universe is part of a larger structure. Signatures in gravitational waves that point to physics beyond the standard model. The multiverse might remain forever unobservable in the direct sense, but if it exists, it could leave fingerprints, indirect evidence, hints, and those hints, if we find them, would be enough to shift the conversation from speculation to science. Until then, we are left with the knowledge that the observable universe is not the whole story, that beyond the horizon there is more, maybe more of the same, maybe something stranger. We do not know. We might never know, but the not knowing is not a failure, it is a feature. Science is not about having all the answers, it is about asking the right questions and building tools to test them. Some questions have answers we can reach, others push up against the limits of what can be observed, and some maybe point to limits that are fundamental rather than technological. Places where the universe simply does not give us enough information to decide between possibilities. That is uncomfortable. It means there are things we might never be certain about, but it is also honest. The universe does not owe us answers. It does not care whether we understand it. It just is. And the fact that we can ask questions, that we can build instruments to probe the cosmos, that we can construct theories and test them against reality is remarkable. We are matter that has become conscious of itself. We are the universe looking at itself and trying to figure out how it works. That is not a small thing. That is extraordinary. And the fact that we have come as far as we have, that we know as much as we do about the structure and history of the universe, is a testament to human curiosity and ingenuity. So what lies beyond the observable universe? More galaxies, probably. More stars and planets and black holes and all the rest. The same physics, the same forces, the same story playing out in regions we will never see. Or maybe something stranger. Bubble universes with different constants, parallel branches of quantum reality, a holographic boundary encoding everything we experience. We do not know. We are standing at the edge of the map, looking out into uncharted territory, and the map ends not because we stopped drawing it, but because the universe stopped giving us information. The horizon is not a wall. It is a limit set by light and time and the speed at which space expands. Beyond that limit, the universe continues. What it contains we can only guess, and maybe that is enough. Maybe the knowing is less important than the looking. The search for understanding, the drive to push the boundaries of knowledge, the refusal to accept ignorance when answers might be within reach. That drive has taken us from a geocentric universe to a cosmos of 2 trillion galaxies, from a static eternal universe to one with a beginning and an accelerating expansion, from a universe made of ordinary matter to one dominated by dark matter and dark energy. Each step revealed something unexpected, each answer raised new questions, and the process continues. The frontier keeps moving, the map keeps expanding. And somewhere out there, beyond the edge of what we can see, the universe is doing its thing. Indifferent to whether we understand it, infinite or finite, unique or one of many, the same everywhere or different in ways we cannot imagine. It does not matter to the universe, but it matters to us. Because we are the ones asking. We are the ones looking. And as long as there are questions left to ask, and tools left to build, and data left to gather, the search will continue. The veil will lift, one observation at a time, one discovery at a time, and the picture will come into focus. Not all of it, maybe not even most of it, but enough. Enough to know that we live in a universe far larger and far stranger than we ever imagined. And that beyond what we can see, there is more, always more. 2 trillion galaxies, 93 billion light-years, 13.8 billion years of history written in light that left its source before Earth existed. We started with a canvas, a bubble of time and space centered on a rock where, for reasons nobody fully understands, chemistry became biology and rocks became us. And we asked, what fills that canvas? What lives in the space between stars and the voids between galaxies and the silent regions where light has not yet arrived? The answer is everything. Gas giants wrapped in storms older than civilizations, black holes warping space-time into knots, galaxies colliding in slow motion over hundreds of millions of years, planets where it might rain diamonds or methane or molten glass, moons with oceans hidden under ice, cosmic rays carrying the energy of a fast ball packed into a single proton, neutrinos passing through the Earth like ghosts, gravitational waves rippling outward from collisions so violent they momentarily outshine the combined light of every star in the observable universe, and threading through all of it, holding it together and tearing it apart. Two invisible forces we have names for but do not understand. Dark matter, dark energy, the missing 95%. We are standing at the edge of the map, looking outward, and the map ends not because we stopped drawing it, but because the universe stopped giving us information. Beyond the horizon there is more. Maybe more of the same, maybe something stranger. We do not know. We might never know. But the not knowing is not a failure. It is an invitation. The universe is not holding back. It is showing us everything it can. The challenge is not seeing farther. It is understanding what we are already looking